request today's president of the workshop, Dr. F.C.
हॅलो
Raghu.
हॅलो हॅलो
Yes, sir.
हा उपस्थित डॉक्टर FC रघुवंशी सर, डीन संत गाडगे बाबा अमरावती विद्यापीठ अमरावती, डॉक्टर कतोरे सर, डॉक्टर गांडोळे सर, डॉक्टर चर्जन सर, उपस्थित सर्व गणिताचे तज्ज्ञ विद्यार्थी आणि शिक्षक मित्रांनो, गेली 4 वर्षापासून गणित विभाग अमरावती विद्यापीठ अमरावती आणि IDI के महाविद्यालय, आदर्श महाविद्यालय आणि मूर्तिजापूर महाविद्यालय हे संयुक्त विद्यमानाने रामानुजन जयंती मोठ्या उत्साहाने साजरी करत आहे आणि त्या निमित्तानं विविध कार्यक्रम आयोजित करत आहे. सर्वप्रथम मी सर्वांना रामानुजन जयंतीच्या शुभेच्छा देतो आणि अशा पॅन्डेमिक सिच्युएशन मध्ये सुद्धा डॉक्टर कतोरे आणि इतर महाविद्यालय मोठ्या हिरिरीने ही जयंती साजरी करत आहे, उपक्रम राबवत आहे आणि म्हणून मी त्यांना शुभेच्छा देतो. विद्यार्थी मित्रांनो, या कार्यशाळेच्या निमित्त, या सिच्युएशन निमित्त मला एक सांगावंसं वाटतं की जीवनातील प्रत्येक पैलू, प्रत्येक क्षेत्र या पॅन्डेमिक सिच्युएशन मध्ये स्वतःला जगवण्याचा, स्वतःला वाढवण्याचा प्रयत्न करत आहे आणि यामध्ये शिक्षण क्षेत्र सुद्धा मागे राहत नाही आहे. असणाऱ्या परिस्थितीत अवेलेबल असणाऱ्या साधनांचा वापर करून शिक्षण प्रणाली अजूनही आपण सुरू ठेवत आहे. यामध्ये शिक्षकांचा आणि विद्यार्थ्यांचा मोठा सहभाग आहे. परंतु विविध अडचणी येतात, कुठे नेटवर्क नसतं, कुठल्या ऍपचा वापर करता येत नाही आणि म्हणून मला असं वाटतं, या निमित्त सांगावंसं वाटतं की विद्यार्थी मित्रांनो, एखादं शिक्षण घ्यायचं आहे, एखाद्या विषयाचं नॉलेज घ्यायचं आहे, जेवढं विषयाचं नॉलेज घेणं महत्वाचं आहे तेवढं जास्तीत जास्त महत्व आजच्या घडीला, कारण ही परिस्थिती अजून किती दिवस राहील कळणार नाही. म्हणून सर्व शिक्षकांनी, विद्यार्थ्यांनी, विद्यापीठांनी आपल्या ICT चा वापर करणे, ICT चं ज्ञान घेणं खूप आवश्यक आहे. जर आपण असं जर केलं नाही तर ही जी शिक्षण घेणारी पिढी आहे ही इतरांपेक्षा वर्ष 2 वर्ष मागे राहील. या परिस्थितीमध्ये ज्या काही विभाग असतात, म्हणजे महाविद्यालय आहेत, विद्यार्थी आहेत, शिक्षक आहेत, विद्यापीठ आहेत, सर्वच जण पहिल्यांदाच अशा संकटाला समोर जात आहे आणि पहिल्यांदाच अशा ICT चा वापर करत आहे. म्हणून प्रत्येकामध्ये काही उणिवा राहत असतील, प्रत्येकाने एकमेकाला समजून घेऊन त्या उणिवा दूर करण्याचा प्रयत्न करू आपण आणि या शिक्षण प्रणालीला तसेच या वर्कशॉपला यशस्वी करू अशी अपेक्षा बाळगतो आणि शेवटी या वर्कशॉपला शुभेच्छा देतो आणि थांबतो. धन्यवाद.
Thank you, sir. May I now request Honorable Dean Dr. F.C. Raghuvanshi sir to deliver a presidential speech and inaugurate the today's workshop. Please.
Chief guest of today's inaugural function, Dr. G.S. Khadekar, Dean, Faculty of Science and Technology, राष्ट्रसंत तुकडोजी महाराज, नागपूर युनिव्हर्सिटी, नागपूर, डॉक्टर Y.D. गांडोळे, प्रिन्सिपल, आदर्श महाविद्यालय धामणगाव, डॉक्टर R.D. देशमुख, प्रिन्सिपल, RDIK कॉलेज बडनेरा, डॉक्टर A.P. चर्जन, प्रिन्सिपल, राठोड कॉलेज मूर्तिजापूर, मेटे, RDIK कॉलेज बडनेरा, डॉक्टर बायस्कर, आदर्श महाविद्यालय धामणगाव, and Dr. Neemkar, Head, Department of Mathematics, Rathod College, Murtijapur. All the resource persons, head and faculty members of the affiliated college, and dear student friends, very good morning to one and all present for this workshop. It's my great pleasure to be with you for the inaugural function of this workshop. Dear friend, if you are interested in teaching at senior college level then you have to pass either NET or SET, or you have to complete PhD degree. Even though you are meritorious at UG and PG level, you cannot apply at the senior college level. To apply this, you have to pass NET SET exam or PhD. If you analyze result of NET or SET, then we find that it is very less. It is negligible. The success rate at national level as well as at a state level, it is very low. Thus, we can conclude that the NET SET is, to success the NET SET is difficult. आपल्या भाषेतच जर सांगायचं झालं तर नाही रे बाबा, हे आपल्या बसचं काम नाही. याला बरेच नेट लागतात. याच्या मागे लागण्यात अर्थच नाही. आपली तर हिंमतच नाही बाबा. परंतु मी तुम्हाला छोटस उदाहरण देतो. मग नेट सेट बाबत बोलू. तुम्ही गोडाऊन किंवा कृषी उत्पन्न बाजार समिती किंवा जिथे ट्रक भरल्या किंवा खाली केल्या जात असते तेथील हमाल पाहिलेच असते. ते पटापट एक क्विंटलचे पोते उचलतात व सहजतेने घेऊन जातात. हमाल तब्येतीने पैलवान नसतो. बरेच हमाल तर कुपोषित वाटतात. आणि जर हेच एखाद्या पैलवानाला सांगितले तर तू करू शकेल अथवा नाही खात्री देता येते. This example show that to get the success in any target, you need skill. Without skill, you cannot success, you cannot achieve your target, your goal. Mathematics Teacher Association, संत गाडगेबाबा, अमरावती युनिव्हर्सिटी अमरावती, Dr. Katore and their colleague have identified this problem, and since last 5 years they are organizing university level workshops on NET or SET guidance in mathematics in collaboration with affiliated college, Darshi Mahavidyalaya, RDIK and Rathod College. Initially, when NET SET exam was started in our university area or even in at state level or national level, the result of NET and SET is very low. In mathematics, it is very poor as compared to other subjects. But as per my information, after this workshop, during last 5 years, more than 50 students have cleared NET SET examination. It is also observed that the cut-off point for the mathematics is increasing every year. as compared to last year, it is more. Even though our students are getting success in net set examination, therefore, I congratulate the chairman of Amravati University Mathematics Association, Dr. Katore, all the members of Mathematics Teacher Association for organizing this workshop. This workshop has given an opportunity to the and they can get guidance, they can get confidence to appear for net set examination and to get success in it. Generally, it is observed that such workshops are also organized in different subjects by some departments or colleges, but it is not a regular practice. Whereas, in this case, regularly organizing the workshop or guidance of NET and TET student, and they are getting results. Students are benefited. This workshop, again, peculiarity of this workshop is organized on the birth anniversary of Indian great mathematician Srinivas Ramanujan. Today is his birth anniversary. We cannot think that the boy at the age of 12 can give some mathematical theorem, and Ramanujan has given a mathematical theorems at the age of 12. I salute to this great Indian mathematician. As a teacher, I have analyzed the success rate of the student in net set examination, and in my opinion, it is not fault of our student. It is a fault of us. It is fault of our examination system. Our examination system is faulty. It is based on memorization and reproduction. You have to memorize and you have to reproduce as it is in at the time of examination. You can memorize a particular topic, and if the same topic appear in the exam, then you can reproduce well and you can get a good result. That we are evaluating you on the basis of mark and on the
सर सर तुमचा माईक झालेला आहे प्लीज माईक अनम्यूट Please,
Hello.
sir.
Hello.
माईक अनम्यूट करा सर तुमचा माईक म्यूट झालेला आहे. हा आता आलाय. आता बोला.
Okay. Hence, our success rate of as thought and understanding. These are the secondary thing. Hence, our success rate in NET and SET is low. You have to develop a skill of understanding of particular topic. Once you understand the topic, you can write anything, you can apply it anywhere. But if you memorize the topic, you will not able to reproduce it after some days. And this is our problem. With this thinking, the Amravati Mathematics Teacher Association has started this activity, and this activity gives very good result. I am confident that this workshop will provide a guidance. This workshop will motivate you. This workshop will give a skill how to understand the topic and how to apply it. The organizer has invited resource persons working in this field. They will guide you and they will give the idea about the NET SET examination. You have to use this for your NET SET examination preparation. And if you prepare as per the guidance of these resource persons, I am sure that you will get success. My best wishes are with you. I thank organizer for giving me this opportunity to share my view with you. I wish a grand success for the success of this workshop, and I wish best luck for the future of the student. Thank you.
Thank you so much, sir, for giving so much valuable information regarding the workshop. May I now request Principal Dr. Y.B. Gandode, sir, to esteem our audience. Please, sir.
A very good morning to one and all those who are joining this workshop. At the outset, I am very grateful to Honorable Vice Chancellor, Honorable Pro Vice Chancellor, Santa Gadgil Amravati University, Honorable Dean, Faculty of Science and Technology, Dr. Raghuvanshi sir, Honorable Head of the Department of Mathematics, Santa Gadgil Amravati University, Dr. Kature sir, Principals of the Deshmukh sir, Charjan sir of the RDIK, and all the principals, then head of the departments of our college, Dr. Bhaskar sir, respected resource persons, all the teachers, mathematicians, and dear students. I would like to take this opportunity to thank the conference organizing committee, Santa Gadgil Amravati University, particularly Mathematics Association, for their consistent hard work for organizing such events in this 22nd day of December every year. Really, they are grateful. The National Mathematics Day that is celebrated on this today, 22nd of December, which is the birth anniversary of Srinivas Ramanujan, an Indian mathematician born to change the future of mathematics. He was never formally trained in the subject, yet he became one of the greatest mathematicians. That is the great thing. His contribution to the mathematics in the field of various dimensions to infinite series, number theory, mathematical analysis, etc. The celebration of the National Mathematics Day started to inspire more youth to pursue their dreams and ambitions. But in spite of this, the Santa Gadagova Amravati University creates the platform for the UG and PG students for preparation of competitive examination, which is very essential for lectureship, that is NETSET examination. So really, I am very much thankful and congratulates the organizing committee. Dear student, I want to share some few views in front of you in this occasion. That is mindset. That is the new psychology of success. That is very important whenever you have to crack any examination. So both these mindset, there are two mindsets, which is one we call it is fixed mindset, and another we call it is a growth mindset. So our mindset, which in which category we belongs to, that we want to change from fixed to growth mindset. So in fixed mindset, which assumes that our character, intelligence, and creative ability are static, which gives we can't change in any meaningful way, and success is the affirmation of that inherent intelligence, an assessment of how those gives measure up against an equally fixed standard. Striving for success and avoiding failure at all costs becomes a way of maintaining the sense of being smart or skilled. That is a fixed mindset. But that fixed mindset, we have to change over it to the growth mindset. So what is growth mindset? So growth mindset, on the other hand, views all challenge and sees failure not as evidence of unintellectual, but as here hurting springboard for growth and for stretching our existing ability. Out of these two mindset, which one means manifest from a very early age, springs a great deal of our behavior, our relationship with success and failure in both professional and personal context, and ultimately our capacity for happiness. So these are the two mindsets which is very essential for your success. So always you change your fixed mindset to growth mindset. And the subject mathematics, which is a very important subject in all science, and once you create awareness, once you create interest in this subject, naturally all the subjects should be very easily to understand and to maintain and to remember and to crack. So that's why I am very much thankful to the organizing committee for giving me this opportunity. Last 4 to 5 years, they are consistent in this program. So I am last but not the least, I am very much thankful to Katore sir, all the organizing committee for these events and giving me the chance to share my views in this regards. Thanks. Thank you very much.
Hello.
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 हा भास्कर सर. हा नेटवर्कचा प्रॉब्लेम.
Hello.
हॅलो. हा सर, तिथे थोडा नेटवर्क प्रॉब्लेम आहे. युनिव्हर्सिटीमध्ये थोडा नेटवर्क प्रॉब्लेम आहे सर.
Okay. Hello. Now there is a, I think so. I call from the, somebody is calling me. Hello. Somebody called me. Actually, there is a network problem in the Amravati University Department of Mathematics. And he told me that, sir, you start your chief guest speech. So, hello, are you listening me? Anybody?
Yes sir.
Can I start now?
Yes sir.
Okay. Very good morning, all of you. I am.
Good morning.
Good morning. I am Dr. G.S. Khadekar, and today's just chief guest of this function. The Dean, Faculty of Science and Technology, and President of the today's function, Dr. F.C. Raghuvanshi sir. Head of the Department of Mathematics and Patron of the today's function, Dr. H.D. Katore. And Dr. Y.B. Gandole, Principal of Adarsha College, Dhamangor Railway. Similarly, Dr. R.D. Deshmukh, Principal RDIK College, Badnera. Dr. A.P. Charjan, Principal Principal Dr. R.G. Rathod College, Murtazapur. Invited speakers, guests, students. The member of Mathematical Society, Sant Gadge Baba, Amravati University. Dr. Vayaskar, Dr. Mete, Dr. Ghate, Dr. Kirde, Dr. Patil. There are two Patil, YD Patil and KM Patil. Dr. V.D. Sharma Madam, all invited speakers, ladies and gentlemen, and my dear students. First of all, I am very much thankful to the organizer who gave me this opportunity to say something in this today's event. Actually, there are two events today coupled by head of the department, Dr. H.D. Katore. The first event is National Science Day. The National Science Day that you know very well. This is the celebrations in the view of the Ramanujan, Srinivas Ramanujan. The everywhere, in whole India, they are going to celebrate. And another program is university level workshop on NetSet guidance in mathematics. So there are the two programs, and in the two programs, the couple in this program, there is two ways, and I am going to share some things before you, and I am going to inspire to the students. Just H.D. Katore told me that, sir, you just give the lecture or you just inspire our student for NET and SET examination related to the NET and SET examination. I am not a big man to inspire to the student, but I will just tell you something related to mathematics as well as related to the NET and SET examination. The Dean Faculty of Science and Technology, Dr. S.P. F.C. Raghuvanshi, giving a lot of things, giving a lot of example, giving lot of, they give in his speech, the inspiration speech, in his inspiration speech, they give a lot of information to the student, how the NET and SET students will go to the success and all these things. And similarly, Dr. Katore told me one of the very important informations in his speech. He told that above 50%, that is 50 plus students getting NET and SET, they are past NET and SET examination in the Amravati region. Actually, basically, I am from the Amravati region, and I know that what is the area and how much is the student is hardworking there. So first of all, I'm very much congratulate to that students. They are just passed this examination. This is a very big examination and success in this examinations in NET and SET. So I told before that this is a couple of two program. That is the first is the National Mathematics Day. Actually, today is National Mathematics Day 2020. This day is celebrated in the view of the well-known mathematician Srinivasa Ramanujan. Today is 133 birth anniversary of Ramanujan. And you know that the Ramanujan is very well known for one of the well-known figure for who knew infinity, the man who knew infinity. So you know that how was the Ramanujan. So I am not giving some lectures on the Ramanujans. You know that what is the history of the Ramanujans and how was the Ramanujan. So actually, if you tell you if I tell about the Ramanujan, then there is a very big lectures I'm going to share with you. But today is not the time, and I will not share a lot of things about the Ramanujan. But I just share one things about the Ramanujan. The Ramanujan is having one number that is a very famous number. That number is 1729. That you know very well what is the 1729. 1729 number is nothing but 1 cube plus 12 cube. That is also nothing but 9 cube plus 10 cube. This is the magic numbers investigated by or discovered by Srinivasa Ramanujan. Apart from that number, Ramanujan also gave the number, another number. That number is 4104. That 4104 is related to the 2 cube plus 16 cube. Also 3 cube plus 15 cube. So these are the history of the Ramanujan. But if you go in the back history of the Ramanujan, in the view of the National Science Day, I will tell you things. Because Ramanujan was not very successful man in his tenure. He was just a clerk in Madras. Nobody can accept the Ramanujan's concept. And one day, I think so, there was a story. One of the college in London, that college was MJM Hill of University College. Ramanujan applied this college for this scholarship. And this college refused the Ramanujan scholarship. At that time, Ramanujan thought that this is not for me. This is not for me. But Ramanujan's, you know that the Ramanujan, how the Ramanujan was success. The Ramanujan success, you get it only because of one person, and that person is G.S. Hardy. The G.S. Hardy gives the chance to the Ramanujan, and the Ramanujan shows his chance, shows his all these things before you. And you know that how was the Ramanujan. So I am not telling about more things about the Ramanujan. Now today, my dear students, this event is again coupled with the one of the very important things that is called university level workshop on NET and SET guidance in the mathematics. If you see about the NET and SET examination, that I will tell you, because being the Dean of Faculty of Science and Technology, I have gathered a lot of data for my university for NET and SET student. This data is not available in my university sometime because the student passed the NET and SET examination doesn't give the data to the university department. And that's why the university department doesn't have any data, because basically you are the student of the university department or any affiliated colleges, And if you are giving the information to the college, or if you are providing the information to the university, okay, sir, I passed this examination in such and such year, in such and such grade, that is NET and state examination, because that data is not available in the university sometimes. So there is my humble request to all the NET and state pass out students also, and those who are going to appear for the student. There is my one request. You please, if you success in the examination, please provide your data to the department. And that's why this data is very essential in NAC and NAC accreditation. Because in NAC accreditations, they requires, they needs. They ask to the departmental head, they ask the vice chancellor, like, how many students pass from your university, these are getting the NET and state examination. These are just success in the NET and state examination. This is one of the data, and that data covers some marks in the NAC. So there is my humble request to all to give your data to the university, because I am going to face the same problem nowadays, because our university is going for NAC in the next month. And we are collecting that data. बरेचशा वेळा काय होतं की मुलं हा डाटा विद्यापीठाला देतच नाही. ते पास होतात, ते सक्सेस होतात, परंतु नेट आणि सेट मध्ये सक्सेस होताना तो डाटा त्यांनी डिपार्टमेंटला दिला पाहिजे की बाबा आम्ही ह्या एक्झामिनेशन मध्ये पास झालेलो आहे, कारण आम्ही तुमचे स्टुडंट होतो, तुम्ही डिपार्टमेंटचे स्टुडंट आहात, आणि डिपार्टमेंटच्या स्टुडंटनी नेट अँड सेट जर पास केलं असेल तर माझी रिक्वेस्ट राहील तुम्हाला की तुम्ही एक मेल करून टाका हेड ऑफ द डिपार्टमेंटला किंवा प्रिन्सिपलला की सर आम्ही या नेट अँड सेट एक्झामिनेशन मध्ये या इयरला पास झालो आहे. तो डाटा विद्यापीठाकडे राहतो आणि त्या डाटाच्या भरोश्यावर नेट अँड सेट एक्झामिनेशनच्या डाटाच्या भरोश्यावर नॅक मध्ये अक्रेडिटेशनला त्याचा फायदा होऊ शकतो. सो एनिवे, सो my dear student, those who are already passed or who are going to face the examinations, there is my request to all of you to do that one. FC रघुवंशी सरांनी एक सक्सेस स्टोरी तुम्हाला सांगितली की कसं सक्सेस व्हायला पाहिजे, हाऊ टू सक्सेस इन द एक्झामिनेशन, हाऊ टू डू फॉर द एक्झामिनेशन. एक त्याच टाईपची स्टोरी मी तुम्हाला एक सांगतो. सो दॅट स्टोरी इज, यश मिळत नाही तोपर्यंत प्रयत्न करणे. मी मित्र हो, तुमच्याच एरियातला असल्यामुळं माझं एक गाव अमरावती पासून 70 किलोमीटरवर आहे. अंजनगाव, सुरजी आणि परतवाड्याच्या मधात मी राहतो. तिथे एक गाव आहे छोटस, त्या गावाचं नाव आहे पांढरी. त्या पांढरी या गावामध्ये रामदेव बाबाचं टेम्पल आहे. मला ती स्टोरी आठवते म्हणून मी तुम्हाला शेअर करतो. त्या टेम्पल मध्ये एक साधू महाराज राहायचे. फार जुनी गोष्ट आहे, जी मला आठवली म्हणून आता सांगतोय. त्या गावामध्ये एक साधू महाराज राहायचे आणि ती वस्तीची, गावाची वस्ती आमच्या गावापासून 3 किलोमीटर दूरवर ते गाव होतं, आणि त्या गावाची वस्ती हार्डली 3-3.5 हजार लोकांची वस्ती होती. त्या गावामधला जो साधू महाराज होता त्या रामदेव बाबाच्या टेम्पल मध्येच राहायचा. इथं अजूनही ते टेम्पल आहे. तुम्ही जर गेलात तिथं शहानूर धरण आहे, त्या बाजूला तिथं एक मोठं टेम्पल आहे. त्या टेम्पल मधल्या साधू महाराजची एक कथा अशी होती की त्यांनी नाचणं सुरू केलं, म्हणजे त्यांनी डान्सिंग सुरू केलं की पाणी पडायचं. ही गावातल्या लोकांची एक कल्पना होती. त्या गावातल्या लोकांना कधी असं दुष्काळ पडला किंवा अशी पाण्याची आवश्यकता पडली किंवा बरेचशा आपल्या एरियामध्ये जर तुम्ही बघत असाल तर पाणी येत नसलं तर 7 दिवसाचा सप्ताह करतात. मग ते धोंडी पाणी दे म्हणून तो बरेचसा त्याचा प्रकार असतो. तो प्रकार केल्यानंतर असं लक्षात येतं की ते पाणी 7 दिवसानंतर पडतं. तर प्रयत्न यांच्या सप्ताहामुळे पाणी पडतं की ईश्वराच्या देणगीमुळे पाणी पडतं की ढग आल्यामुळे पाणी पडतं, ही कल्पना वेगळी. कल्पना अशी होती की तो साधू महाराज, मित्र ही गोष्ट तुम्ही काळजीपूर्वक ऐका, तुमच्या लक्षात येईल. तो साधू महाराज जेव्हा नाचायचा त्यावेळेस पाणी पडायचं. साधू महाराजांनी नाचणं बंद केलं की पाणी पडायचं नाही. असंच दिवस चालत गेले. एक दिवस 4 तरुण MSc मॅथमॅटिक्सचे, त्याच्यामध्ये नेट सेट देणारे पोरगा, ते त्या गावात गेले. ते गावात गेल्यानंतर त्या गावातल्या लोकांशी त्यांनी चर्चा केली. म्हणे आम्ही असं ऐकलंय की तुमच्या गावातले लोक, एक साधू महाराज ज्यांनी डान्स जर केला तर पाणी पडतं असं होतं. अशी ही खरी गोष्ट आहे काय? ते मॅथमॅटिक्सचे लोक, मॅथमॅटिक्सचे पोरं, त्यातले काही रिसर्चर होते, ते चारही लोकांनी गावात पूर्ण फिरून एक माहिती काढली की हा साधू महाराज काहीतरी लोकांना बनवतोय. ते फिरले गावातल्या प्रत्येक माणसाने सांगितलं की नाही, ही कल्पना नाही आहे. आम्ही साधू महाराज जवळ जातो आणि साधू महाराज जेव्हा डान्स करतात तेव्हा पाणी पडतं. ही कल्पना ऐकून ते चारही मॅथमॅटिशियन जे होते त्यांचे विचार बदलले. तो म्हणाले का मूर्खपणा आहे. मॅथमॅटिशियन कांट डू दॅट वन, कांट बिलीव्ह ऑन दिस थिंग. म्हणून ते चारही गृहस्थ साधू महाराजकडे गेले. की साधू महाराज म्हणे, आम्ही असं ऐकलंय की तुम्ही डान्स केला की पाणी पडते. आता आम्ही डान्स करतो म्हणे, आणि आम्ही डान्स केल्यानंतर पाणी पडायला पाहिजे म्हणे. आता साधू महाराज म्हणाले की ठीक आहे म्हणे, बघ तुम्ही डान्स करा, पाणी पडते की नाही बघा. तर त्यातला पहिला व्यक्ती डान्स करायला लागला. त्यांनी 10 मिनिटं डान्स केला. 10 मिनिटानंतर असं लक्षात आलं की पाणी नाही पडलं. मग त्यातल्या दुसऱ्या व्यक्तीने 1 तास डान्स केला. त्याच्या लक्षात आलं की हा 1 तास डान्स केल्यानंतरही पाणी पडत नाहीये. मग राहिलेल्या 2 यांनी सुद्धा डान्स करणं सुरू केलं. त्यांच्या ते लक्षात आलं की पाणी पडत नाहीये. आता साधू महाराज घाबरून गेले की पाणी पडत नाहीये. मग साधू महाराज म्हणाले की असं राहू द्या, तुम्ही काय डान्स करू नका, मी डान्स करून बघतो, आणि मी जर नाचायला लागलो तर बहुतेक पाणी पडेल. आणि साधू महाराजांनी नाचणं सुरू केलं. ती कल्पना आहे, ती विचार करा तुम्ही. ते मंदिरी आहे तिथे. मी जर काही तुम्हाला असत्य गोष्ट सांगत असेल, एकदम अंजनगाव सुरजीजवळ पांढरी नावाचं गाव आहे, तिथे आहे ते मंदिर. त्या मंदिरातला साधू डान्स करता करता असं लक्षात आलं, संध्याकाळ झाली तरी पाणी पडलं नाही. थोडा वेळ झाला, रात्रीच्या 7 वाजल्याने ढग आले. ढग आल्याने कडाक्याचा पाऊस पडला. इतका जोरदार पाऊस पडला की ते चारही मॅथमॅटिशियन जे होते ते हप्प झाले. म्हणजे हे कसं काय शक्य आहे? आम्ही सकाळपासून डान्स करून आलो, पाऊस पडला नाही. साधू महाराजांनी प्रयत्न केला, पाऊस पडला नाही. परंतु हा नाचत गेला, थांबतच नव्हता. आणि नाचता नाचता असं झालं की ढग काळे झाले आणि पाऊस पडायला लागला. त्या चारही लोकांनी साधू महाराजांना विचारलं, साधू महाराज, तुम्ही खरंच सांगा म्हणे, हे काय कला आहे, तुम्ही काय केलं? मी काहीच केलं नाही म्हणे. माझ्या मनात एक जिद्द होती की जोपर्यंत पाऊस पडत नाही तोपर्यंत नाचत राहायचं. बेटा म्हणे, या लोकांचा माझ्यावर विश्वास आहे म्हणे, या गावातल्या लोकांचा माझ्यावर विश्वास आहे. त्यांना असं वाटतं म्हणे की मी डान्स केला की पाऊस पडतो, आणि ते सुदैवाने मी जेव्हा जेव्हा डान्स करतो तेव्हा पाऊस येतो. यांचा माझ्यावर अटूट विश्वास आहे आणि माझा विश्वास त्या देवावर आहे. मी काहीही केलं नाही. मी फक्त एक प्रयत्न केला आणि त्या प्रयत्नातून असं झालंय की ते घडत गेलं. मित्र, जेव्हा तुम्ही काही नवीन काम करता, या स्टोरीची मॉरल ऑफ द स्टोरी काय असायला पाहिजे, जेव्हा तुम्ही काही नवीन काम करता तेव्हा अनेक वेळा अपयशीच पदरी पडते. पण त्या अपयशातून काम करण्याचा प्रयत्न आपण बंद करून टाकतो. आपलं अपयश आलं म्हणजे आपण बंद करतो. नेट सेटची पहिली परीक्षा दिली आणि आपल्याला मार्क मिळाले नाही तर आपण काय करतो, जाऊ द्या म्हणतो, कशाला जायचं याच्यामध्ये, आपण नाही पास होऊ शकत. त्याच्यापेक्षा आपण पीएचडी करू, 3 वर्ष गाईडकडे राहू, 3-4 पेपर पब्लिकेशन करू चांगल्या इम्पॅक्ट फॅक्टर जर्नलमध्ये, आणि आपल्याला पीएचडी मिळाली म्हणजे आपण सूट होऊन जातो. म्हणजे नेटसेट करायची आवश्यकता नाही. मित्र, आता नंतरच्या याच्यामध्ये तुम्हाला पीएचडी विथ नेटसेट राहणार आहे. म्हणजे तुम्ही त्याचा विचार करा. गव्हर्नमेंट तुम्हाला नोकरी देताना बऱ्याचशा गोष्टी टाळणार आहे. होऊ शकते पीएचडी विथ नेटसेट होईल. नवीन एज्युकेशन पॉलिसीमध्ये जर गेला तर ती पॉलिसी तर अजून भयानक आहे. खूप चांगली पॉलिसी आहे ती. म्हणजे त्या पॉलिसीवर जर विचार केला तर ती विचित्रच पॉलिसी आहे असे वाटते कधी कधी, आणि ती खूप चांगली पण पॉलिसी आहे. त्याच्यामुळे पीएचडीचा प्रोग्राम त्याच्यामध्ये राहतो, एमएससी मॅथमॅटिक्स त्याच्यामध्ये राहते, की वेगळ्या टाईपचे कोर्स येतात, दॅट आय डोंट नो. मित्र, या साधूच्या गोष्टीवर जेव्हा मी प्रकाश टाकतो, जोपर्यंत यश प्राप्त होत नाही तोपर्यंत आपण नाचत राहिलो तर पाणी पडतं. म्हणून मित्र, मला या स्टोरीमध्ये तुम्हाला यश सांगायचं आहे की जोपर्यंत तुम्हाला यश येत नाही ना तोपर्यंत अपयशाची भाषा तुम्ही बोलूच नका. तुम्ही हे समजूच नका की मी फेल झालो, म्हणून मी पुढची एक्झाम देणार नाही. तुम्हाला एक साधं एक्झाम्पल पुन्हा सांगतो मी, की एका मुलाला पहिल्या टेस्टमध्ये 120 मार्क मिळाले. त्याला असं वाटलं की मी त्याच्यापेक्षा जास्त घेऊ शकतो, म्हणून त्यांनी दुसऱ्या टेस्टचा अभ्यास केला. त्यांनी हे समजून की मला 240 मिळतील. परंतु जेव्हा त्यांनी दुसऱ्या परीक्षेला अपिअर झाला तर त्याला फक्त 8 मार्क जास्त मिळाले, म्हणजे 120 चे 128 झाले. तुम्ही हे समजू नका की तुम्ही ज्यावेळेस दुसरी टेस्ट द्याल त्यावेळेस खूप चांगलं प्रयत्न करायला आणि खूप चांगले मार्क मिळतील असंही होत नाही. इथे अपयश येऊ शकतो तुम्हाला तिसऱ्या राऊंडलाही अपयश येऊ शकतो. परंतु ते जर बंधनकारक तुम्ही सोडून दिलं तर मग तुमचा मार्ग खुपून जातो. म्हणून तुम्ही प्रयत्न करत जर राहिलात तर तुम्ही यशस्वी होऊ शकता. आणि तुमच्या जीवनाचा एक सर्वात महत्वाचा मार्ग मी तुम्हाला सांगतो. मला एक पटोले सरांनी खरं तुम्हाला आज जे इन्फॉर्मेशन दिली की 50+ स्टुडंट तुमच्या इथले नेट अँड सेट झालेले आहेत. आणि त्या 50+ माणसांना जेवढे आहेत त्यांना मी कॉंग्रॅच्युलेट करतो की अशा एरियामध्ये तुम्ही राहताय, त्या एरियामध्ये तुम्ही 50+ मध्ये पोरं या नेट अँड सेट एक्झामिनेशन मध्ये पास झालेले आहे. सो दॅट इज वंडरफुल फॉर द युनिव्हर्सिटी. It is wonderful for the region also. You get it this 50% and above students, 50+ students are passing NET and SET examination. I will not take more time. मित्र हो, की आपण ज्या मार्गाने चालतो आहे, आपल्याला जे आपल्याला जो मार्ग आपल्या समोर दिसतोय त्या मार्गाने जाण्याकरता सोपं नसतं. UPSCच्या एक्झामिनेशनला बसताना 12 लाख लोक बसतात. त्या 12 लाख मध्ये 15 लाख बसणारे असतात, पण 3 लाख लोकांजवळ पैसे नसल्यामुळे ते बसू शकत नाही. 12 लाख पैकी जेव्हा रिझल्ट येतो ना तर 9 लाख फेल होतात. ते किती दुःखी असतील. जे 15 असतात ते 15तले 12 बसतात ते 3 किती दुःखी असतील. त्यानंतर 12 लाखापैकी 9 लाख जे फेल होतात आणि 3 लाख पहिल्या टेस्ट मध्ये पास होतात ते किती दुःखी राहत असतील. ते आपला मार्ग सोडत नाही. पुन्हा तुम्ही नेक्स्ट एक्झामला त्या UPSCचं जर गेला तर तुम्ही याचा स्टॅटिस्टिक्स केलेला आहे म्हणून तुम्हाला सांगतो. 3 लाखपैकी हार्डली 50,000 पोरं सक्सेस होतात. ते पुन्हा बाकीचे दुःखी राहतात. आणि त्या 3 लाख पैकी जे 50,000 सक्सेस होतात त्या 50,000 मधले नेमके 1000 पास होतात. आणि त्या 1000 मधले जे फर्स्ट IAS ऑफिसर किंवा मोठ्या पोस्टवर जाणारे जे असतात ना मित्र, ते फक्त 10 किंवा 15 असतात. त्या 10 मध्ये आणि त्या 15 मध्ये दुःखी असणारे लोक असतात. हे की जे पास तर झालेले आहेत पण त्याला पोझिशन चांगली मिळाली नाही. पास तर झालेले आहे पण त्यांची जम्मू काश्मीरला कुठेतरी अपॉइंटमेंट झालेली आहे. तेही दुःखी असतात. यातला सुखी कोण असतो? म्हणजे IAS झालेला आहे, IPS झालेला आहे, UPSCच्या एक्झाम पास झालेला आहे, तो पास करून आलेला आहे, एवढ्या पायऱ्या चढत आलेला असून सुद्धा तो दुःखी असतो. त्याच्यापेक्षा आपण सुखी बरे. आणि मला हेच म्हणायचं आहे, पायरी गाठताना प्रत्येक ठिकाणी अडथळे येऊ शकतात. मग आपण जर त्या अडथळ्याला मात करत गेलो, त्या अडथळ्यातून पुढचा मार्ग काढत गेलो तर मित्र तुम्हाला खोटं सांगत नाही, ते खूप सक्सेस होऊ शकतो. आजच्या या दिवशी आपण रामानुजनचं नाव घेतो. त्या रामानुजनला किती त्रास झाला होता. तुम्ही एक द मॅन हू न्यू इन्फिनिटीचा मूव्ही जरी बघितला, जर रामानुजनचं लिटरेचर वाचलं नसेल तर त्याच्यामध्ये त्यांनी बरोबर सगळं त्यांनी केलेलं आहे. किती त्याला त्रास होतो, तो किती त्रासातून पुढे जातो आणि जगाच्या समोर असा इतिहास ठेवतो जो अजूनपर्यंत अनसॉल्वेबल आहे. रामानुजनचे काही फॉर्म्युले अजूनही सॉल्व्ह झालेले नाहीये. असा विद्वान या जगाला आपल्या दिशेने दिला. त्याची आज 133वी जयंती आहे. मित्रहो, मी सॅल्यूट करतो या माणसाला. मध्यंतरी मी काल पेपरमध्ये आपल्या संत गाडगे बाबाबद्दल मोठं विचित्र ऐकलं होतं. कुणीतरी ऑब्जेक्शन घेतलं की गाडगे बाबा जे होते ते राष्ट्रसंत तुकडोजी महाराजांचे शिष्य होते म्हणून अशी कुठल्या तरी पुस्तकात आलं. कुणी राणाने ते पुस्तक लिहिलं. मित्र, या वादात न पडल्यापेक्षा त्या माणसाचं काय कॉन्ट्रीब्युशन होतं या देशाकरता, या रिजन करता, ते आपण लक्षात घेतलं पाहिजे. म्हणून गाडगे बाबाला मी सॅल्यूट करतो की त्या माणसाचंही या रिजन मध्ये फार मोठं कॉन्ट्रीब्युशन होतं. त्यांनी मॅथमॅटिशियनला जन्म नाही दिला, पण त्यांनी ज्या समाजाला जन्म दिला, ज्या समाजाला शिकवण दिली, ती आता लोक वापरत आहे. स्वच्छतेची शिकवण लोक आता वापरत आहेत. त्यांनी तर त्या काळात दिली होती. म्हणून ह्या ग्रेट विजनरीला मी सॅल्यूट करतो. आणि आजच्या या कार्यक्रमाला आपण सर्वांनी मला बोलवलं त्याबद्दल मी ऑर्गनायझरचे धन्यवाद व्यक्त करतो. आणि जाता जाता एवढंच सांगतो फक्त की मित्र हो, या पुऱ्या सिनेरिओ मध्ये, या पॅन्डेमिक सिच्युएशन मध्ये आपण बरेचशा फेजेस मधून आज गेलेलो आहोत. आणि आताच कालची एक न्यूज आहे की रात्री 11 ते सकाळी 9 पर्यंत, सकाळी 6 पर्यंत पुन्हा लॉकडाऊन होणार आहे किंवा त्याला कर्फ्यू लागणार आहे असं म्हणतात. कारण UK मध्ये पुन्हा सेकंड फेज सुरू झालेला आहे कोरोनाचा. त्याच्यामुळे तुम्ही या बाबतीत थोडं सावध राहा. आणि या आजच्या दिवशी युनिव्हर्सिटी लेवल वर्कशॉप नेट सेट गायडन्स इन मॅथमॅटिक्सला मी या लोकांना कॉंग्रॅच्युलेट करतो की त्यांनी अशा टाईपचा प्रोग्राम ऑर्गनाईज केला इन द व्ह्यू ऑफ नॅशनल मॅथमॅटिक्स डे और इन द व्ह्यू ऑफ द बर्थ अॅनिव्हर्सरी ऑफ द श्रीनिवास रामानुजन द ग्रेट मॅथमॅटिशियन. या सगळ्या मेंबर्सला मी पुन्हा धन्यवाद देतो आणि मी इथेच थांबतो. थँक्यू व्हेरी मच टू ऑल ऑफ यू. थँक्यू.
We are really sorry for the inconvenience. Thank you so much, Honorable Chief Guest, Dr. G.S. Khadekar, sir, for your valuable expertise. Thank you, sir. May I now request Dr. S.N. Baiskar, sir, to propose vote of thanks.
Firstly, I tribute to Srinivas Ramanujan, Sant Gadge Baba, and Chhatrapati Shivaji Maharaj. The last part of the inaugural function is vote of thanks. Firstly, I would like to thank Honorable Dr. F.C. Raghuvanshi sir, Dean, Faculty of Science and Technology, Sant Gadge Baba, Amravati University, Amravati, for his valuable guidance. I also thankful to Chief Guest Dr. G.S. Khadekar sir, Dean, Faculty of Science and Technology, Rashtrasant Tuploji Maharaj, Nagpur University, Nagpur, for sharing your valuable guidance in your busy schedule. I also thankful to the Principal, Dr. R.D. Deshmukh sir, Principal Dr. Y.B. Gandoli sir, Principal Dr. Charjan sir, for your support to organize such type of event in university level. Thank you, sir. I am also thank to Dr. S.D. Katore sir for your moral support for last 5 years to organize such type of activity in 22nd December in last 5 years. I also thank to Dr. Mete sir, Dr. Nimkar sir, Dr. Malle madam, Dr. Rangari madam, Dr. Dhore sir, and all faculty members from various colleges join this event. And also thankful to all student participants to join this event. Thank you.
Participants for sticking to time. Before we start session, let me explain how you can talk to us during the webinar. If you have any questions during the presentation, just write them to chat box. We will have a question answer session at the end of the session to answer your questions. Thank you. Now we move towards our first session. May I now request resource person for the first session, Dr. S.R. Chaudhary sir, to impact their knowledge on today's workshop. Please, sir.
नाही सुरू झालं सर येत नाही तर मग करून घेऊ आपण. हॅलो हॅलो हॅलो
Sir, yes,
Yes,
sir.
you are audible, sir.
can you hear me?
Yes, sir. Yes, sir.
Yes, okay. I'm very much thankful for the organizing committee, especially Professor Katore sir, for inviting me to share my views in this NetChat workshop. Actually, my lecture was at the last because I'm going to talk on field theory, right?
तिथे व्हॉट्सअप नंबर आहे.
Because of we have another lecture session from our university.
व्हॉट्सअप आहे ना, तुला ऍड करून तिथे ग्रुपवर. तिथे फोटो नाही लागून, फोटो आहे, फोटोचे आणि इथे साइन कर.
Rearrange my lecture for him. But as in the inaugural session, Professor Khadekar sir said, the people, those who have already done some contribution in the past, right, which is now now we can see that it is important for us, and nowadays it is useful for us. So whatever work they have done in the past, that is useful. So one of the greatest personality, Dr. Mr. Srinivas Ramanujan, who has done his work in 1887 to onward for 33 years, is now using in computers and at many fields. So in the beginning, let me just briefly introduce him. Might be you people are already aware. Srinivas Ramanujan was from a poor family, as you all aware, and at his matriculation level, he was very talented. But when he reached to the intermediate examination, he was very much interested in mathematics only. So he was good in other subjects also, but because of he was interested in mathematics only, he was doing calculations for mathematics only. He was doing his calculations for mathematics only. But the result of that is he was got failed in mathematics, and he was able to pass only mathematics. Other subjects he has failed. So he was failed 2-3 times, and he was interested in mathematics only. So his interest was reflected at many places and at many events, and some of his colleagues, some of his friends has requested the mathematicians of the world that he should be given a chance to do mathematics. So G.H. Hardy, there is a big story behind all these things, but I am giving you a brief. So G.H. Hardy was a man who has seen his research papers, which he has sent to Hardy. And then he has found that some of the results are very much new, and some of them are already reported by some other people. At the beginning, he thought that whatever work is shared by Ramanujan, probably maybe it may be copied from somewhere or something of that sort. But some of the results were very much new because he was working in that field. So he was in confusion state in the beginning. So, but he expressed his view that he want to discuss with him about more topics or more concepts on that. And then he found that actually Ramanujan found that Ramanujan is talented person. He has no formal education of mathematics, but he has done some good mathematics. That is what he has seen, right? And then he think that we should give Ramanujan technical knowledge of mathematics, and then we can do some work. So he has invited him to there in Cambridge. Ramanujan went there, and working with him, taking the technical knowledge. They both have Hardy and Ramanujan have done some research, very much research, I mean, and that was known to the world. So because of Hardy, you can say Ramanujan was known to each of us. At the age of 33, he was died at a very small at a small age, right? When he was even on the verge of his last stage, and Hardy came to meet him that time. Hardy said that I came from a taxi whose number was 1729, and which is, I think, is a dull number. But Hardy, but Ramanujan at that last stage also, he said that no, this number is very important number. This is the smallest number which can be expressed as a square of powers of two different in two different ways of the integers, right? Square of primes of two integers in two different ways. So that number is like this. So his very much interest in mathematics can be seen from that at the last stage also, and he was died at the age of 33. So we tribute to him, and on the eve of this, your school has organized a workshop for NetSet. So I think this is a very nice idea from them, right? So let me start for my technical lectures on this, as it is expected from me that I should talk on some objective questions from either past of NetSet question papers. So I have collected some of the questions and I will guide you on this. So you can see the first question, which of the following is not a field? It is a very simple one and everybody knows about it, but we need some guidance about it. We can see that when we say that a ring is a field, so we know that it should be a commutative ring with unity in which every non-zero element has a multiplicative inverse. This definition is known by everybody. But the important concept is a commutative ring with unity. So you can see that twice z is nothing but set of all integers, even integers. So it starts from 0. 1 is not there, but 2 is there, plus minus 2 is there, and then plus minus 4 is there. So multiples of 2, I mean 2z. So you can see that 1 is not there, and 1 acts as a identity for integers, multiplicative identity. So unity means 1. So which is not present in that. So this satisfies all the conditions, we can say, but it is not satisfying. It do not have a identity. So it is not a ring with unity. So therefore it is not a field. Even you can have inverse, whether it is inverse is exist or not. Even inverse is not exist. It's a multiplicative inverse. So that part is comes later. So twice z is not a field. But we know that q, r, c, r, these are the field, right? So 2z is the simplest point which is not a field, right? We can see this is the answer for that. And in the second example, you can see which of the following statements is false. Which of the following statements are, particularly I will concentrate on field theory only. So questions from field will be there, because other resource persons will take lectures on maybe their topic group theory and ring theory and linear algebra. So I will concentrate on field theory. So which of the following statement is false? There is a field with 7 elements, there is a field with 100 elements, there is a field with 125 elements, and there is a field with 16 elements. If you remember in a field theory course, we have a result that there is a field with p raised to n elements where p is prime and n is any natural number, right? Natural number greater than or equal to 1, right? So when p is prime and n is greater than or equal to 1, so the numbers are prime p, p square, p cube, and so on. So for primes, p, their squares, their cubes, and their any order, any natural order, right? So we can see that out of this answers, we can have first is 7, the third is 125, and the fourth is 16. So 7 is written as 7 raised to 1. So it is a power of a prime, right? And then 125 is also 5 raised to 3. And 16 is also 2 raised to 4. But 100 is not able to express as the power of a prime. And we have proved the theorem also. The field of these powers p raised to n are exist, and not only that, these are the only fields. There is no other field, no other order field is exist, and those fields are unique also. So that order field is unique. So when there is a field of order 7, then there is only one field. There will not be two different fields. We know that the groups are 2. So suppose you take of order 4. So in group theory, we have 2 groups of order 4. One is Z4 and other is the Killian 4 group, V4, if you remember, clean 4 group, right? And that clean 4 group is V4. And we know that Z4 is abelian, but V4 is not abelian, right? Not cyclic, I mean, not abelian, not cyclic. So Z4 and V4 are the 2 examples of group. But in the case of field, we have only one field of order p raised to n, right? So out of these three objectives answers we can have, second is the option where field is not exist, right? So that second will be the correct option for this problem, right? We can take the third one. F is a field with say, just a minute. Okay. Field with 27 elements. So F is a field with 27 elements. Which of the following is true? That is what we have to. So F has no field, subfield. F has no subfields. F is a field with 27 elements. Now we are saying that it has no subfield. Second one is F has subfield with 1 element, subfield with 3 elements, and subfield with 2 elements. As I told you, the fields are exist of power prime only, right? And 27 is the power of 3, right? So the subfield is a subgroup basically. When we go for a subfield, those are subgroups also. And when there is a group of order at 27, there should be a subgroup whose order must divide order of that. So we know the Lagrange theorem. So that 3 is a number which divides 27. Which of them is true is this one. So field with 3 elements is there, right? There is a possibility of field with 1 element also. But that can be treated as a trivial one, right? So that's why we will say that third is the proper answer for this. The number of subfields of a field of order 3 raised to 10 are, how many subfields are there of order 3 raised to 10? If you remember the field theory course, in which we have a lattice diagram of subfields, and that is basically now again I will repeat the same theorem. When there is a field, the order is p raised to n. So here 3 raised to 10. So power of a prime. So prime is 3 and 10 is there. And the divisors of power of prime are always the power of that prime only. So that means powers of 3 raised to 10 which are divisors of 10 we can say, right? Or we can say divisors of 3 raised to 10. So how many divisors are there for 3 raised to 10? So 3 raised to 0, that is 1 is trivial. 3 raised to 1, that is 3. 3 raised to 2, 3 raised to 3, you can go like this. That means you can find divisors of 10. So how many divisors of 10 are there, that you can find, right? So divisors of 10 you have to concentrate. So how many divisors are there for 10? So 1 is a divisor, 2 is also a divisor, 3 is not a divisor, 4 is not a divisor, 5 is a divisor, and then lastly 10 is a divisor. So how many are there? So total divisors of 10 are 4. So 3 raised to those orders. So those are the subfields of field of order 3 raised to 10. Right? So 3 raised to 1, 3 raised to 2, 3 raised to 4, and 3 raised to 5. These are the divisors. These are the orders of the subfields. Therefore, there only will be 4 subfields. So sometime in this question, the word proper subfields will appear. Instead of only subfields, proper subfield word will also appear. So when we say proper subfield, so 3 raised to 0, right? That is 1. So that you have to exclude. 3 raised to 10 we have to exclude, right? 3 raised to 10 we have to exclude. That you have to, the last one. So this will be 3 then in that case. If it is proper, if somebody asks you how many proper subfields are there, then there will be 3, because 3 raised to 10 you have to exclude. So it is not a proper subfield, right? But here it is not a proper subfield. It is not asked to give you proper subfields. All subfields it is asked. So these are 4. So therefore, the C option is the correct option for this problem. If R is a field of finite characteristic n, then n is what? In ring theory, we have studied a theorem that when there is an integral domain, what is the characteristic of that? But basically, what is characteristic of a ring? Characteristic of a ring is the smallest positive integer n, smallest positive integer. So it should start from 1 onward, so that satisfying the condition n into a is equal to 0 for every a. Multiple n into a. N into a means a plus a n times. So addition of the same integer n times. So smallest n such should be there. How many times you can add a number element of that ring? Smallest time, so that the addition will be 0. That means additive identity, right? So in a field, in an integral domain, if you remember the theorem is like this. In a ring, in an integral domain, the characteristic is either prime or a 0, right? 0 or a prime. And we know that every field is nothing but integral domain. So that is applied to field also, right? So field also have a characteristic either 0 or a prime. And you can see that in the question itself, n is not equal to 0 is given. So R is a field with finite characteristic where n is not equal to 0. So that 0 possibility is already excluded. So only alternative remains is a prime number. So even number, odd number, and natural number, that will not be the answer. Only prime number will be the correct answer for this problem, right? So you have to consider that theorem. So in integral domain, the characteristic is always either prime or 0. So this is applied to field because every field is an integral domain. So whatever we'll consider for integral domain, that will be true for this one, for the case of characteristics, right? So this one is there. So C is the correct answer for this. Fx is a Fx is a polynomial ring over a field F. So F is a field, and in which we want to discuss the result, right? Fx is a polynomial. So ring of polynomials in X. The coefficients are from F. So ring of polynomial over a field F. Which of the following is false? So you concentrate on whether it is asked true or false. Sometimes it is asked false and sometimes it is asked true. So concentrate on whether it is asked true or false. Here it is asked which of them is false. So 3 of them are correct, right? So this question can be considered as a multiple answer question also. If it is asked which of the following is true, true, there are 3 answers. But it is asked now which of them is false. Fx is the integral. So when F is a field, then Fx is nothing but an integral domain. It is not a field, right? And the simplest verification for this is if you consider X as a polynomial in Fx, what should be the inverse for that? Because in Fx, the constant polynomial 1 is nothing but an identity, right? So therefore, when we take X as a polynomial, the inverse will be 1 by X only, so which is not a element in that. That's why you can have it is not an integral. It is not a field. So Fx is the integral domain always. When F is a field, Fx is the integral domain. So this is applied to Q also because Q is field. So Qx is the integral domain, not a field. R is the integral domain. Rx is not a field, right? So that can be applied. For particular examples, we can get it now. But this is the standard result. When F is a field, then Fx is the integral domain. It never be a field, right? Second one is Fx is the equilibrium domain. What is the definition of equilibrium domain? In equilibrium domains, we can say that ring R is called a integral domain is called the equilibrium domain. If there is a function which is defined from non-zero elements of R to a positive integer, which is having the properties. The first property is the valuation, the delta mapping. Suppose delta is a mapping from R minus 0 to Z plus Z union 0, you can say. And that should satisfy the two conditions. The first condition is this delta of xy should be greater than or equal to delta x. And the second condition is the property of division algorithm should hold, right? So this Fx should satisfy the property of division algorithm. That means for every a and b, when b is not equal to 0, you can divide by b to a, right? So there exists q and r, so a is equal to bq plus r, where r is a number either 0 or less than the valuation of that element b, right? That is what we do. That is the definition of equilibrium domain. So Fx is equilibrium, and for that you have to verify whether such a function is exists. So what is the positive number? Because we want a delta is a mapping from non-zero elements of Fx to positive integer. So what number is associated with polynomials? That we have to find out and whether that will be give you a resultant function. So for polynomial, the number associated with it is only the degree, and which is also a non-zero degree and which is also a positive. So for every polynomial, there is a degree as a number, which is non-zero number. So if you define a mapping delta as delta of fx is equal to degree of the polynomial, a degree of fx, then that number is always a positive integer. Sometimes it may be zero. So that whether it will be satisfied, we can see that delta of fx into gx, because it is in the integral domain, fx and gx are polynomial fields that is an integral domain. The result is a degree of fx is equal to degree of fx plus degree of x. So delta of fx into gx is degree of fx into gx, and which is something a degree of fx plus degree of gx. So this means that which is greater than or equal to degree of fx. So that means delta of fx is greater than or equal to fx, degree of fx, right? So that is satisfied. And the second condition, the division algorithm is hold in polynomial in a field, right? So therefore, it is true in fx also. The only thing, important thing is in equilibrium, that condition, the second condition and division algorithm is, in division algorithm, we have that Q and R, quotient and remainder are unique. Whereas in this Euclidean domain, the remainder and the quotient Q and R are not unique, right? That part is not there in. But in this case now, in polynomial, we are getting the unique Q and unique R. So we are not asked whether it is unique or not, but that should be one information you should know, right? So in fx, satisfies the fx in which fx both the conditions are satisfied by the function delta, which is degree of fx, and therefore this fx is also equilibrium, right? So whenever f is a field, then fx is equilibrium domain. That is another result, right? And f is a field already given, so fx is the equilibrium domain. So therefore, the third answer is also a correct answer, right? That is a true answer, but we are asked false answer. Okay. Again, f is the field and fx is the principal ideal domain. Or you can have every equilibrium domain is the principal ideal domain. So if you remember the relation between equilibrium domain, principal ideal domain, ED, PID, and UFD, then we can have every ED is a PID, every PID is a UFD. And already we are saying that fx is the equilibrium domain. So obviously it is a principal ideal domain also. So B, C, D are the true answer, but we are asked the false answer, and that is the first one, right? I'm giving the information for other options also because of sometime the question may be like this. So in which we can get that hint so that we can answer the question. So that's why I'm explaining, right? Which of the following is true in 7th one, right? Rx upon x square by 5 is a field. Qx upon x square minus 5 is a field. Cx upon x square minus 5 is a field. And the last one, there exists irreducible polynomial in Px with multiple roots, right? Irreducible polynomial is existing in Px with multiple roots. That is what we can. Okay, so to show that the quotient ring is a field, R by I is a field. If you remember this in ring theory, then I is ideal, and then R by I is a field when it is a field. We have a result R by I is a field if and only if I is a maximal ideal, right? So that is the result. So in this case, if you are able to prove that the ideal which is given in the numerator of the first three options, whether it is ideal, whether it is a maximal ideal or not. And in ring theory, we have if the polynomial is irreducible, then the ideal generated by the polynomial is nothing but maximal ideal. So what we have to check the polynomials which are given in the ideal, whether they are irreducible polynomial or not. When we say the polynomial is irreducible, it should not have a factor in R. For the first example, for the first option, or in second, we have it should not have roots in Q, and in the third case, it should not have roots in C. That is what we can have. Now, x square plus 5 in Rx. So, what are the roots of that polynomial? X square minus 5. X square minus 5 is equal to 0 if you take, then x is equal to under root of plus minus 5. So, the roots are rationals, irrationals, and both the root 5 and minus root 5 are there in R. So that means this polynomial is reducible, right? So that means the ideal generated by that polynomial is not a maximal ideal, and therefore it is not a field. So the first option is not correct option. We'll go to the third option also, okay, instead of going to B. Now you take the third option, x square minus 5. What are its roots? Those are rational roots, irrational roots, and which are there in complex. Every real number is a complex number. Imaginary part is 0 that way. So therefore, if it has a root in R, obviously it has a root in C, right? So this third option is also is a correct option. That is C of x upon x square under ideal generator by the field, because ideal generator x square minus 5 is not a maximal ideal in this case also. Now in a key in the last option we require a theorem, and the theorem is like this: when there is a field with characteristic 0, right? When there is a field with characteristic 0, and if there is irreducible polynomial, then it should not have a multiple root. That result is there in field theory. Now here Q is a field with characteristic 0. So characteristic of Q is 0. And polynomial is given as a irreducible polynomial. Suppose there is a polynomial that you can consider, then the irreducible. So you should not have multiple roots. So it contradicts to that theorem. So whenever there is a field with characteristic 0, irreducible polynomial in that ring of polynomials should not have multiple. That was the reason. So this last statement contradicts to that theorem, and therefore this is also not true. Whereas in Qx upon x square minus 5, B option you can say, the roots of x square minus 5 are under root plus minus 5. Those are irrationals which are not there in Q, because Q contains rationals only. So this polynomial is irreducible over Q, and therefore ideal generator x square minus 5 is the maximal ideal, and therefore the quotient root is the field. Therefore B is a correct answer for our this example. Which of the following is correct? So B is the correct answer. Let us go to the next one. When I is ideal in a ring R generated by x square plus bx plus c, then the quotient ring R by is a field if and only. We know that the ideal generated by this one is a maximum ideal. Or you can say that root should not be exist in R. Right? That is what we have. So when roots are not exist, that is what we have to verify. And the simplest one is that b square minus c less than negative is there, then square root is not exist. So therefore, this will be the answer for this. Right? So that way you can take that. So that is a simple one. Again, this ninth example, I1 is ideal generated by x raised to 4 plus 3x square. I2 is ideal generated by x cube plus 1. If F1 is Qx upon I1 and F2 is Qx upon I2, then which of the following? Just a minute.
नेटवर्क पहा मला नेटवर्क नंतर मग तुम्ही मनस्पतीशी कॉन्टॅक्ट करा. हो तिलके सर ते मनस्पती शिंदे सर यांच्याशी कॉन्टॅक्ट करा.
Okay, if F1 is Qx upon I1 and F2 is Q2 upon I2. Now again I1 and I2 are ideal generated by the polynomials. The same reason we can apply it. Ideal, when the ideal is maximal ideal, then only this quotient is a field. Now I1 is generated by x raised to 4 plus 3x square plus 2, and I2 is generated by x cube plus 1. Now whether this polynomial is irreducible, now that you have to check, right? And if they are not irreducible, then the ideal is not maximal ideal, and the answer will be, you can find, right? So whether you check that whether I1 and I2 are maximal ideal or not, or you can check that the polynomials are irreducible or not, right? Now you can say that x cube minus 1. So this is a polynomial having complex root, you can say, right? And complex root will not be there in Q, and therefore the second polynomial is irreducible, right? So it should be a maximal ideal in QX. So second should be a field. I think the answer is here it is misinterpreted. B is not that answer, right? So because x cube plus 1 is irreducible over Q, so that should be a field. F2 should be a field. And you can find F1 has a roots in Q. So that is not a maximum ideal, and therefore F1 is not a field. So F1 is not a field, but F2 is a field. That is the correct answer. That means C is the answer for this one. For 9, C is the answer. Or you check it, whether it has the roots or not. If roots are not there, obviously this x cube plus 1 has complex roots. So that is not a correct answer. C is the correct answer for this, right? And you can apply the same result. So you can check it yourself, whether it is correct or not. The similar example is there, x square plus 1. Next example, I1 is ideal by x square plus 1, and I2 is example this one. And here we can see that x square plus 1. So x square is equal to minus 1, you can say, right? X square is equal to minus 1. So you can find whether it has a root or not, right? This x cube minus x square plus x minus 1, right? Check it whether the polynomials are reducible or not. I'll take a minute. We have some.
ते तुम्ही पण कम्युनिकेशन्स मध्ये राहता या ठिकाणी.
Okay, so you check it whether the first polynomial and second polynomial is reducible or not. When if they are reducible, then the question ring is the ideal. So similar problem you can have. Probably the answer might be incorrect. One of my students has find out those. So in that sense, I'm talking. You check it whether the polynomial is reducible. Sir, I'll take just 5 minutes. Now next, the degree of the field extension R over Q. Degree of the extension is defined like this. Suppose E is the extension of F, then the degree of E over F is nothing but the dimension of E over F, because when E is the extension of F in field, then E is always a vector space over F. So whenever we have extension, we have a vector space. So whenever extension is there, vector space is there. If the dimension is exist, and the number of element and dimension is called the degree of the extension. So this R is a extension of Q. We know this. Both are field and Q is contained in R. So R is an extension. So degree of R over Q we can find as a vector space. And if you remember, then the basis of this is uncountable, right? You might have already proved it. So R over Q has a basis which is uncountable, right? It is an uncountable element. So obviously it is infinite. If it is given, suppose C over R instead of R over Q, then we know that the set 1 and I, the two numbers, right? That is nothing but a basis of C over R. So this C is the extension of R, having basis is having two elements. So in that case, the dimension is 2. But in the case of R over Q, we have a result that the dimension of R over Q is uncountable, right? In the vector spaces we have. And when it is uncountable, the number cannot be countable. So obviously infinite elements will be that, right? Correct option is infinite. 1, 2, 3, they are not the answer. D will be the answer. The number of fields properly lying between R and C. How many fields are exist in this one? Most of the times we are not aware about the fields rather than Q, R, and C, right? And at the most ZP when P is prime. These are the only examples people are aware. Whether there is a field. So in number field system, we know that Q is contained in R, R is contained in C. But in between, whether the fields are not there or not. And we have a result in field theory that we can take an element in the extension. Now here we can say C is the extension of R. So you can take an element in the extension and we can adjoint it with the smaller field. So we can take a complex number here and we can adjoint with R. We will get a field between these two, right? But if it is a proper field, then only properly lying, it is asked properly lying. And if you take any complex number x plus iy, and if you try to adjoint with R, R adjoint with x plus iy, then it is nothing but complex, right? So even you can take I, simplest complex number Ri, then it is also complex. So for this case, when C is the extension of R, when we adjoint the element from complex to R, you will get a complex itself. So there is no field between R and C, because when you try to adjoin, you will get an X field. So therefore, between R and C, there is no field properly lying. So that will be the answer. None of this is the answer, because answers are here 1 to n infinite. So there is answer. But suppose in case instead of this R and C, it is given R and Q now. In the above example, we are R and Q. Suppose here R, Q and R, because R is the extension. So any number which is not there in Q, you can add adjoint with Q. So Q root 5. Q root 5 is not Q. It is not equal to real, because other real numbers are not there. Q root 5 or maybe some root 7, 7th root 5. These are the elements which are not there, or even other real numbers will not be there. So in case of Q or R, the answer will be infinite. Whereas over this R, between R and C, there is no field which is properly lined, right? So there is another example we can say Q or R, then it is infinite. But here R or C, none of this is the answer, right? No field is there which is properly contained between the both. This R is a proper subfield of C, but it is not R. It is R properly lying between them. Properly, it is not R, it is not C. Between them, there is no. How many proper subfields are there for C? Then there is one. That is not one. There are others also. Infinite, right? But between R and C, there is no, right? Because Q is also a proper subfield of C, and any element, real number which is adjoint with Q, that is also a proper. So Q root 5, Q root 2, Q cube root of 7, and when adjoint with them, these are the subfields of C that we can have. So those would be proper when we say how many proper subfields of C are there. That is asked. Between it is not there, then there are infinite. But between these two, there is no. Okay. Let K be extension of Q. So here also it is given Q. So the extension of Q is either real or when we adjoint some element from real or maybe from complex, that will be the extension. Zi is one example of that. Qi you can take. Okay. So when K is extension of a field Q, which of them is which of the following is correct one? K is a finite extension, then Q is an algebraic extension. K is algebraic extension, then it must be a finite extension. K is algebraic extension, then it must be infinite extension. K is a finite extension, then it need not be an algebraic extension. So we have already the result that every finite extension of any field is algebraic. Every finite extension is algebraic extension. That right? Algebraic extension need not be a finite extension. That will. So that result can be applied to this, and we can find the answer. First one is also correct, right? First one is correct. Any finite extension is always algebraic extension. That we have. So C over R is an extension having degree 2. It is finite, and therefore C is an algebraic extension of R. You can say like this. So here is particularly taken Q, but it's not necessary. You can take any field F. Then the result is also true. Which of the following ring is unique? Unique factorization domain. This is for a ring theory question, but because it involves field, so I had taken it, and I want to tell you something about it. So that's why I did. Which of the following ring is a unique factorization domain? In unique factorization domain, what is the definition? The definition is every non-zero, non-unit element should be expressed as a product of primes in a unique way, right? Unique product should be unique. So every non-zero, non-unit should be expressed as product of primes in a unique way. That is what we mean unique factorization. PID means what? It should be every idea should be a principal idea, right? That is what we are. And as I told you, every ED is contained in PID. Every PID is contained in UFD. That sequence we can. Or every ED is PID. Every PID is UFD. So ED is PID. PID is UFD. So that is what we are. So PID is always UFD, but it is as reverse. Unique factorization, but not PID. And that containment is always proper. That means there is an example of a PID which is not a IED. There is an example of UFD which is not a PID. So particularly it is asked which of the following is giving the reverse is not true. That is what it is asked. If you remember the Gauss lemma in ring theory, particularly D is the integral domain, then dx is the integral, d is the integral domain, or d is UFD, then dx is UFD. That is what we are Gauss-Lehmann says. So z is a unique factorization domain because every non-zero, non-prime, non-zero, non-unit. Non-zero means non-zero integer, and non-unit. We express a product of prime unique way. We know in Z. That is a fundamental theorem of algebraic, right? So for Z it is 2. When F is a field, then Fx is a PID. We know this. F is a field, Fx is a ED, so therefore it is PID. In last example also, yes. So Fx is a ED, and therefore it is PID. But it is asked, it is not a PID, but it is already PID. So this will not be the correct one, right? Then this Zi, the last option, Zi. We have seen that this is the ring of Gaussian integers. So complex number is a plus bi, where a, b are real. Where Zi is a plus bi, where a and b are integers. So instead of other rationals and irrationals, we can have this. So Zi is a plus bi, where a and b are integers. So ring of Gaussian integers is this side. And there is a standard result in the ring theory that Zi is always a ED, Euclidean domain. And we know that ED is PID, PID is UFD, so Zi is also PID. So that is also not correct one. So only alternative remain is ZX. So that way also you can find the answer which is not true, right? ZX is not a PID because ideals in ZX are not principal ideal, right? So ZX is not a PID. This is a standard example in ring theory also. ZX is not a PID. You can have ideal generated by some polynomial is not a PID. That is that example you might have encountered earlier. So ZX is not a PID, but is a UFD because Z is a UFD, so ZX is a UFD, right? Z is UFD, so ZX is by Gauss-Lehmann. So ZX for this example, say 15, V is a space over the field F3, 3-dimensional vector space over field F3, Z upon 3Z. That means Z3 it is, right? 3 elements, field 3 elements. The number of distinct one-dimensional subspaces of V, how many are there? So this for this the answer is 13. So you have to do some little mathematics for this, and you can get this answer. So I will leave it up to you, but the correct answer is 13. Okay, in which of the following field the polynomial is irreducible? Right? Which field it is? It is irreducible. Right? So that we can see this. So I have calculated it with the help of a MATLAB program that it has no root in Q, but it has a root in F3, F13, and F7. So therefore, the last answer is the correct answer. So little bit calculation you have to do for this also, and you can check it. So it has no root in Q, and therefore this one is no, it has a root in Q. So therefore, D is the correct answer, right? And no other element in F3 we can have 0, 1, 2. Only these elements. So we put 0 for x, 1 for x. You can say that these are the one of the root is, right? So that way you can see this. Okay, let us go to the next one. Let omega is a complex number such that omega cube is 1 and omega is not 1. Suppose L is a field q root 2 omega generated by cube root 2 and omega over the field Q of rational numbers. Then the number of subfields K of L such that Q is properly contained in K and K is properly contained in A. So now here you can see the omega cube is 1. So this is cube root of unity, I mean. Right? If we simplify it, we know that it is -1 by 2 plus I root 3 by 2. Right? That is omega is this one. Whose cube is 1. Cube root of unity. And which is a complex number. So this we are adjoining. In Q we are adjoining omega as well as the irrational number cube root 2. Right? So two numbers are adjoining in that. Cube root 2 and omega. Right? So we are getting an extension of Q. So cube root of 2 omega is extension of Q. Right? It is generated by it is said. These two are adjoined with Q. That also you can say. Number of subfields K of L such that they are properly between Q and L. Right? We have seen earlier that between how many subfields are there, right? So here we have two fields, Q and Q, cube root of 2 omega. So these are the two. How many will be raised in that you have to find out. So it is related to the degree. There is a result in field theory related to the degree. So you can see that it will be 4. So in which there are 4 fields will be there in that. So little bit that theorem you have to concentrate and do the little bit calculation. You will get that there will be 4 fields properly between Q and this L. L means this one. Q cube root of 2 omega. So 4 will be there in that. Right? Okay. Consider the polynomial fx is this. X raised to 4 minus x cube plus 14x square plus 15x plus 16. Also for a prime number p, fp in the field with prime element. So this is a polynomial and fp is a field with p elements. Which of the following are always true? Which of them are true? There are 3 answers for this. I had taken it from recent question paper. That considering f as a polynomial coefficient in f3, it has no root in f3. It has no root in f3. That is what it says. So you can put the value of x as 0, 1, 2. We can check it. 0 is not a root. Obviously 16 coming. 1 is also is not a root. That when putting this, we can simplify. This is the number which is non-zero. For 2 also, this fx is not equal to 0. So therefore, there is no root in that. Right? So this is also a correct answer. Similarly, considering f as a polynomial coefficient f3, it is a product of 2 irreducible factors of degree root 2 or f3. So it cannot be expressed as product of 2. So that is also a correct answer. It expresses product of 2 polynomials. Those are irreducible. That is what. Similarly, considering f as a polynomial coefficient f7, it has irreducible factor of degree 3. For this, there is a result. There is always a irreducible polynomial or finite field. Now here it is irreducible factor. The factor is or not. That is. So you can calculate that factor, find the root, and then calculate that. So this is also correct. The last one is not correct. F is a product of 2 polynomials of degree 2 or z. In z, it is not coming because there is no root in z. Fine. Right? And degree 2 polynomials. So when we take degree 2 polynomials in z, we will not get like this. So therefore, you take 2 polynomials and simplify it. So this is not coming. So A, B, C are the correct answer for that. This one is a little bit tricky. The degree of the extension q root 2 plus q root 2 or q root 2. I think might be there is a printing mistake, or maybe this question is tricky, but I don't get it actually what it is. As it is, I have taken the degree of the extension q root 2 plus q root 2. When we add q root 2 plus root 2, this will be 2 root 2, right? Root 2 plus root 2 is 2 times 2 root 2. No? So 2 is an element in q, so this is nothing but a q root 2 itself, right? So q root 2 plus root 2 is nothing but q root 2. So the degree of this extension is r itself. So that's why the answer is 1. If it is root 2 plus 3 root 2, then the answer is different. So I think they have made some mistake. Instead of root 2 plus root 2, it is root 2 plus root 3. Right? So you have to find out a polynomial satisfying that element, root 2 plus root 3. And that is a 4-degree polynomial that we have. And that extension is of degree 3. That 3 is the answer when it is root 2 plus root 3. But whereas it is root 2 plus root 2. So this is 2 root 2. So it is nothing but q root 2. So therefore, field with it over itself. Every field with itself has a basis containing a single element, that is the identity, or any non-zero element you take, single will be the basis. Any non-zero single element is a basis of field over itself, right? Simplest one is multiplicity identity and take, because we don't know whether non-zero elements are exist or not, other elements, but one is always there. Therefore, singleton one is always a field, but any non-zero element, single element also give it a field when it is exist. So it is asked here q root 2 or q root 2, so the answer is 1, right? I think it is little bit tricky, I suppose. Otherwise, the answer will be different. Okay, let f be equilibrium domain such that it is not a field. So it is equilibrium domain but not a field. Then polynomial ring is always each of them. Then the polynomial ring is always equilibrium domain. Then principal ideal domain but not equilibrium domain. Unique factorial domain, not a principal. Unique factorial domain but not a unique factorial. Equilibrium domain which is not a field. So such an example if you have in mind, then we can get it. This is same thing as the previous example, which is already there. Same thing, but only the revised one. This one, 14 number you can say. Here also we have UFD but not PID, right? UFD but not PID. It's the same thing in a different wording, right? This is the same problem, right? We should have an example which is equivalent domain but not a field, and that is nothing but Z. Z is ZD, but it is not a PID. We know. Simplest example we know. So unique factorial domain. ZX, I mean, you can take instead of Z, you can take ZX. ZX is the equivalent domain which is not a field. So ZX is unique factorial domain because Z is unique factorial domain, but Z is not a ZX is not a PID. So C is the correct answer for this. The rest of them are, because only one answer is there, so rest you can verify yourself. Which of the following question ring is a field? We have already encountered a similar problem. The only point here I want to express you, the polynomial x square plus x plus 1, you have to see that whether it has a root in F3 or not, right? Or it has a factor in F3 or not. Because it is 3, you can just check 0, 1, 2, put it there and check it. If you put 0, then it is 1. If you put 2, what will say that you can check it. And whether this polynomial is irreducible polynomial. So here there are 2, x square plus x plus 1 is reducible over Q because the roots are complex. And in field F2 also 0 and 1 is not satisfying this because for 1 it is 3, for 0 it is 1. So therefore it is not reducible over F3. So in that case C and D are the correct action, right? And x minus 3, obviously 3 is the root of that polynomial and therefore it is reducible over ZX. So P is not answer. And similarly in F3 we can put, I think 2 is the answer for that. So it is reducible over F3 also. That's why C and D are the answer, right? Okay, this is also related to a result. It is K over F, field extension of degree 6. Then the Gallais group K is isomorphic. So this is the standard result is there in the standard book that it is cyclic group of order 6. So that's why the answer is this, right? Permutation group on order, permutation group on 1, 2, 3 is of order. Permutation group we have to find. So it is 6 by 3, 6 by 2. It is 3. So it is a group of order 3. So it is not order 6. Therefore it is not the answer. Right? And similarly for permutation group on 6. So 6 factorial divided by 2. So that is a big number which is not again 6. So that's why that is. And the last one is not obviously it is a permutation group. T is not a trivial group. So that's why that it is a group of order 6. So first is the answer. The group S3 of permutation acts on a 3-dimensional vector space of a finite field of 3 elements by permuting the vectors 1, 2, 3 by the definition sigma into EI is equal to sigma suffix EI, right, for all sigma. So this is the action of a group on a set. Action of a group on a set. So that is what. So group is S3 and acting is given by basis. So sigma into EI, where EI is nothing, E1, E2, E3. So that is the basis. And sigma suffix EI means what? That suffix of EI is changed by that rotation, right? The cardinality of the vectors, the fixed field. The fixed field of the degree of the fixed field of it should be calculated. Fixed field of G. So here the fixed field of G is 3 because when we permit when fixed means what? Under this action, which element kept fixed? So image will be the same, right? Image will be the same. So when we take sigma as identity, that time E1 will map to E1, E2 will map to E3. So there will be only 3. So 1 map to 1, 2 map to 2, 3 map to 3. So that is the only alternative. 1 map to 2, 1 map to 3. It's not fixed. So that's why the answer is 3 for this, right? So B is the answer for this. What is the number of non-singular matrices over F2? So this is little bit, I have not calculated it, but the answer is 168 for this. So you can do some little calculation and you can find. Okay, now this you can see. Let F be a field extension. Let F be a field extension of a field K. So now F is extension, and AB belongs to a algebraic over K of degree Mn and respectively. Which of the following is true? Now here this is the standard result in field theory that A and B are algebraic over field of degree Mn and what is the thing, right? Here it is asked which of the following is true. A plus B is algebraic over K of degree Mn, M plus N. A into B is algebraic over degree Mn. A minus B is algebraic over K of degree M minus N. A by B is not equal to 0, algebraic over K of degree at most Mn. We have a result when A and B are algebraic over F of degree Mn, then the field extension F of AB adjoining A and B are adjoined with the F round bracket AB is the extension of degree at most Mn. At most Mn. And at most Mn are finite. So Mn is also a finite number when Mn are finite. So this extension F of AB over F is a finite extension, and every finite extension is algebraic extension. So F of AB, when we adjoin AB, K of AB, when we adjoin AB with K, here the extension is F and the field is K. So K of AB. So K of AB is an extension of F, is an extension of K also, and which is a finite extension of K because the order is at the most Mn. So K of AB is a finite extension of K, right? And therefore it is algebraic extension. That means every element of K of AB is algebraic over K. Every element of K of AB is algebraic over K. And K of AB is a field containing A and B. So when field containing two element A and B, addition, multiplication, division will be there in that field. So K of AB contains A plus B, A minus B, A into B, A divided by B when it is exists, right? So these elements A plus B, A into B, A minus B are algebraic over K of degree at most Mn, right? But here it is given A plus B is algebraic of degree Mn, M plus N, AP is M into N, like this only. So instead of that, we have at most Mn. It is not necessarily M plus N always. It is not necessarily multiplication of M into B, it is Mn. Similarly for M. So the last answer is the correct answer because A by B when B is null is the element of K of AB. And the degree of K of AB is at most Mn, that means finite, so algebraic. So every element of that K of AB is algebraic over K. So A by B is algebraic over K of degree Mn. So that from standard result we can have this. Consider the polynomial fx is equal to x cube plus x plus 1 in F2. The splitting field of fx over F2. Now we can have this polynomial in F2. So here the point is, see the polynomial is irreducible or not over F2. Now the polynomial is this one. When you put 0 in F2, we have two elements 0 and 1. So you put 0, answer is 1. So it is not 0. So 0 is not 0. And when you put 1, its value is 3. 3 in modulo 2 is 1. So this is again not 0. So both the elements of F2 are not root of. So this polynomial is irreducible. And when this polynomial is irreducible, the field extension of the F2, the element in number of elements in F2 field, that is 2, and the degree of the polynomial that you have to take 2 raised to 3. When we take field with 2 raised to 3 element, then that will be the answer. This is a shortcut I am telling you, but actual result in field theory is like this: if F is a polynomial of degree n which is divisible over a field Fp, then F of p raised to n is the splitting field of that polynomial, right? So this polynomial is divisible Ft, so 2 raised to 3 is the number that we have to take for field. So F2 raised to 3 is a field which is a splitting field of this polynomial, right? So that means its roots are all the roots are exist in F2 raised to, so F8 I mean field with 8 elements, right? Which is exist. Okay, so here because here it is coming field with 8 elements, so I will give you one simple thing which is there in field theory. We have seen that field of prime orders are exist, right? P raised to n. So when those numbers are not prime, so we can see 2 square, that is 4. So field with 4 element is exist because it is 2 raised to 2, power of a 2. So field is there. power of a prime is always exist. So filled with 4 elements, filled with 8 elements, filled with 9 elements, they are exist. Even though they are not prime numbers. But when you take 6 is number, F6 you can say. 6 is not a power of prime. So no such field is exist. Right? So F6 will not be a field. Right? So that also you can keep in mind. So if is a field extension of K and if is a finite field having Q elements, which of the following is not true? Right? So F is a fleeting field of x raised to 2 minus 0. This is true. This is the result, standard result. This polynomial is there in x cube minus x and its fleeting field is q raised to m. Because F is filled with q, m elements. K has q raised to elements for some m. So that we can obtain from this. This is the first result of field theory, that when subfield having q element, then the superfield have powers of that, and the power will be the degree of that extension. So that's why K has q raised to element for some m, where m is nothing but the extension of that subfield over K, right? That is what we can. So K has q raised to m elements. This will be the correct answer for this. And the rest of them are true statements. This x raised to q minus x over K as a is splitting field is there. Then q is p raised to m, that is also because p is a characteristic. A raised to p. All these are results in field theory which are in the beginning part only. Right? If you have studied this, they are from standard theorems. So we did not have to do some calculation. Just statement you have to see and you can get the answer. How many fields are exist for 17 raised to 9? This is power of a prime, 17 raised to this, and there is unique. So obviously only one field is exist. That means they are isomorphic. I mean, only one means isomorphic up to only one. So all are isomorphic. So unique field you can say. There may be two different fields of same order. Elements may be different, but they are isomorphic. So that's why you can say only one isomorphic. Unique one. Let P be a prime. Every finite field with Q is equal to P raised to n elements is isomorphic splitting field of what? Now just we have seen here. You can see first answer A is F is a splitting field with Q raised to x raised to Q minus x over K. The first option A of example number 27. The first line you can see. So that is nothing but this answer. X raised to Q minus over F. Right? So that is the answer for this 29 problem. So I think this is from my side. If you have difficulties or any queries, we'll discuss. Otherwise, so these are the some problems that I have taken is from set question paper as well as net question paper. There are so many, but for the case of field theory, there are very little problems are there in those. So I have taken whichever is possible that I had taken. Some of them might be missing because I have seen very few question papers of set and net, and I have taken that, right? I haven't tried their answer to find. So I think from my side, these are the problems I will share with you. If there are corrections, I have pointed out one correction that you have to make. I think from my side is over. Organizers can discuss with the student if they have some queries.
Thank you, sir. Now it is a session for question and answer. You can clear your doubts in this session. Please ask question if anyone have. Any questions? Participants, please ask the question if you have any queries.
Or otherwise also, you can share my mobile number or email address. If they have some queries and they can send me either by phone or by mail, I can satisfy them. I can give them a time, definitely.
Okay, sir. If they want, we will provide them your number or email ID, sir.
Number or email address, you can
Yes.
contact me. And if somebody is asking, then it is very good. Otherwise, they can send me by mail or by phone. So
Okay, sir. Looks like sir answered all your questions. No one have any queries. Thank you, sir. The way of presenting the field theory in such interesting manner is very inspiring, sir. Thank you so much, sir, for the presentation. Thank you. Now we move towards our second session. May I now request resource person for the second session, Dr. J.N. Chaudhary sir, to address the gathering with your valuable expertise. Please, sir.
Yes,
Thank you, sir.
just a minute.
Okay, sir.
Hello.
Yes, sir.
Whether screen is visible?
Yes, sir. Screen is visible.
Yes. Okay. First of all, I am thankful to organizer committee and HOD Professor Dr. Katore for giving me chance to talk in the NetSet workshop. I will be talking about number theory and the questions which were appeared in either set or net or gate examinations. So in fact, I have divided the questions in three parts, that divisibility, GCD, LCM. Next is arithmetic functions and congruence theory. So start with first question, which was appear in 2013. What is the smallest positive integer in the set 24x plus 60y plus 2000z, where x, y, z are integers? And note that if there are four options, there may not be a guarantee that only exactly one option is correct. Maybe two are correct, maybe three correct, and so on. So what will be the smallest positive integer in the set 24x plus 60y plus 2000z, where x, y, z are integers? Options are 2, 4, 6, 24. You might have known a result. If D is the GCD of two numbers A and B, then it can be written as AX plus BY, where that D is the smallest positive integer. And this will be true for any n number of elements. So here X, Y, Z are integers, 24, 60, 2000 are fixed integers. So this is a combination of three integers. And I want to find smallest combination. So it is exactly that result. D is the GCD of 24, 60, 2000. Then that D is the smallest positive integer of this type. So it is sufficient to find GCD of 24, 60, and 2000. And you check GCD of 24, 60, 2000 is 4. So 4 is the smallest positive integer of such type. So answer is B. Next is a function fn is defined as sum of digits of n. then to calculate sum of digits of 2 raised to 7, 3 raised to 5 and 5 raised to 6, this product. So first you have to find what is this number. But if you try to find 2 raised to 7, 3 raised to 5, 5 raised to 6, and then take the product and then take the sum of the digits of that number, it will be a lengthy job. But observe that this 2 raised to 7 and 5 raised to 6. So base number product is 10. 2 into 5 is 10. So if I write 2 raised to 7 as 2 into 2 raised to 6, then combine 2 raised to 6 and 5 raised to 6 together, it will be 10 raised to 6. And 10 power anything become 1 and then next are 0, 0, 0s. So 10 raised to 6 multiplied by 2 multiplied by 3 raised to 5. So it is sufficient to find the number 2 into 3 raised to 5. And 3 raised to 5 is 243. 243 multiplied by 2, that is 486. And 486 multiplied by 10 raised to 6 will be 4860000 and so on. So sum of digits of that number will be 4 plus 8 plus 6. 4 plus 8 plus 6, that is 18. So here trick is try to collect terms which will become in powers of 10. So answer is 18, that is B option is correct. This was appear in GATE JEE and it depends on sum of first n natural numbers. Here A is a element from the set 1 to n, and 1 plus 2 plus 3 plus n minus 2a minus 1 is equal to 400. Then to find the value of A, just you observe that this equation contains two variables, n and A. So you can't have any tick or direct solution to find value of n as well as A. So in fact, in number theory, such type of equations belong to Diophantine equations. But without using Diophantine equation, we solve this problem by considering sum of first n natural numbers. So come to this equation. We have 1 plus 2 plus dot dot n minus 2a minus 1 equal to 410. It means 1 plus 2 plus so on plus n equal to 2a plus 1 plus 410. And we know left side, it is sum of first n natural numbers, that is n into n plus 1 by 2 equal to 2a plus 1 plus 410. Note that it is given that A is a natural number belong to this set. So 2a plus 1 is positive. So 410 plus positive quantity must be greater than 410. So n plus 1 by 2 must be greater than 410. It means n into n plus 1 is greater than 820. Now see the left side. Left side is a product of two consecutive numbers. And I need product of two consecutive numbers which is just greater than 820. So what will be such a smallest number? It must be 29. You can check. 29 into 30 will be greater than 820. So if n is 29, what will be A? So come to A. n is equal to 29. 29 into 30, that is by 2, that is 29 into 15. Now 29 into 15 is how much? $435. 435 minus 410 becomes 25. 25 minus 1 become 24. So 24 will be 2A. It means A is equal to 12. So A is equal to 12 is the correct option. But there may exist another value of n such that n into n plus 1 is greater than 820. So that number is 30. So 30 into 30 plus 1 is greater than 820, and come to 1 again. 30, 31 by 2, that is 31 into 15. Now 31 into 15 is 465. 465 minus 410 becomes 55. Minus 1, that is 54. 54 equal to 2A. It means A is equal to 27. So 27 answer is also correct. What about another number? If I take n as 31, still 31, 31 plus 1, that is 31 into 32 is greater than 820. But if I consider n as 31, by using 1, value of A will be larger than 27. In fact, larger than 30. And larger than 27, number is not appearing in the options. So there are two correct options, 12 and 27. 12 and 27, that is A and D. And this is not a straightforward problem, so you have to work by using some technique. Next. If n, e, t are distinct positive integers such that product n, e, t is equal to 2013, then which of the following is the maximum possible sum of n, e, and t? Here 2013 is a product of three distinct numbers. So try to find such a product. So first we will find prime power factorization of 2013. You can check here, prime power factorization is 3 into 11 into 61. And these are three distinct positive numbers whose product is 2013. So for this case, n plus e plus t become 3 plus 11 plus 61 is equal to 75. Is it the only possibility? No. Because if I consider 11 into 61 as a one number, 3 as second, and third as 1, you will get product of three numbers. So see, 1 into 3 into product of these two, that is 671. So this is n, this is e, this is t, and their sum is 675. Again, I can consider 3 into 61 as one number, 11 as second number, and 1 as third number. So next possibility is 1, 11, and product of 61 and 3, that is 183. And here sum of digits become 195. Similarly, final case, 1 into 61 as it is and 11 into 3. In this case, sum of digits is 95. And you have to choose maximum among them. So maximum is 675. So our answer is 675, that is C. Which of the following numbers is a perfect square? So if you note, if n is a square number, then its last digit will be either 0 or 1 or 4 or 9 or 6 or 5. So out of these 4 options, B and C, sorry, B and D, here last digit is 2 and in D last digit is 8, and that digit doesn't belong to this set. Therefore, definitely B and D are not the square numbers. So possibilities A and C. But it is difficult to check whether this is square or this is square. So let us use some another technique. Here last 2 digits in 26. Last 2 digits number is 26. So this number is divisible by 2 but not divisible by 4. And hence the complete number is divisible by 2 but not divisible by 4. Now this is not divisible by 4. It means perfect square contains powers of 2 which are even. But here power of 2 will be odd only. That is 1 or 3 or 5. And if power is odd, that number cannot be a perfect square. So by this observation, you conclude that first is a perfect square without testing the number. So this is not the perfect square, and hence rest of the numbers must be a perfect square. Let S be the set of all integers from 100 to 999, which are neither divisible by 3 nor divisible by 5. Then to find number of elements in S. Now this question must have a unique answer, because number of elements in S, if that set is finite, it must be unique. So how will you solve this problem? First, we find all numbers which are neither divisible by 3 nor divisible by 5 from 1 to 99. Then we will find all numbers from 100 to 999 which are neither divisible by 3 nor divisible by 5. So let us see how to find that number. Denote A is equal to set of all integers from 1 to 299 which are either divisible by 3 or divisible by 5. Now, how many numbers from 1 to 99 which are divisible by 3? It can be obtained by considering integral part of 99 by 3. How will you define integral part of the real number? Integral part of the real number x is the largest integer which is smaller than or equal to x. So 99 by 3 is 33. So it is actually integer. So integral part will be 33. So there are 33 numbers from 1 to 99 which are divisible by 3. Similarly, there are integral part of 99 by 5 numbers which are divisible by 5, and it becomes 19. But there may exist some numbers which are divisible by both 3 as well as 5. And as 3 and 5 are prime numbers, those numbers must be divisible by 15. So all the numbers from 1 to 99 which are divisible by 15 equal to 99 by 15 integral part, and it is 6 point something. So integer must be 6. Now, numbers which are divisible by 15 are counted in second as well as in first. So total number from 1 to 999 which are either divisible by 3 or multiplicable divisible by 5 must be taken as 33 plus 19, and all those numbers which are counted twice must be removed. It becomes 46. So here A is the set of integers from 1 to 99 which are either divisible by 3 or 5. So if I take complement of this set, you will get number of integers from 1 to 99 which are neither divisible by 3 nor divisible by 5. So it will be number of elements in set 1, 2 up to 99 minus this, that is 53. So there are exactly 53 elements from 1 to 99 which neither divisible by 3 nor divisible by 5. On the similar lines, we can find number of elements from 1 to 999 which are neither divisible by 3 nor divisible by 5, and you check this, answer is 533. So 533 is the number of integers from 1 to 999 which are neither divisible by 3 or 5. 53 is a number of integers from 1 to 99 which are neither divisible by 3 nor 5. We need number of integers from 100 to 999 which are neither divisible by 3 nor divisible by 5. So you must take difference of these two, and difference of these two is 533 minus 53, that is 480. So option A is correct. Now come to arithmetic functions. This Euler's function is a well-known arithmetic function. It is defined as the number of integers less than or equal to n which are relatively prime to n. That is known as phi n, Euler's function phi. So find the smallest number y such that y into 56361 is a perfect square. So this problem is simple. Just you have to find value of 5361 and that number multiplied by y should be a perfect square. So let us say phi n is the number of positive integers which are less than or equal to n and relatively prime to n. And this is the formula for phi of product pi power alpha. Of course, this is the pp of prime power factorization, and it is product I equal to 1 to k pi raised to alpha minus pi power alpha minus 1. And if I take pi power alpha minus 1 outside, you will get this. Now 5361 is 519 square, and 5 of 19 square by using this will be 19 square minus 1, that is 19 just into 19 minus 1. So 19 into 18. 18 is 2 into 3 square. So this is 5361. Now I want to multiply this number by y so that resulting product is a perfect square. So this is already perfect square. So if we multiply by 2 and 19, that become 38. So 38 into 38, that is 38 square. So total will be a square number. So value of y will be 38. Here, y is 38 into this become a perfect square. So answer is C. This needs some results, counter examples. If x, y are integers and x is less than y, then which of the following is true? Whether 5x is always less than to 5y, 5x is always less than 5y, 5x is always greater than 5y, or no one is true. So here I will show A, B, C are not true by showing and counter examples. So here 5 is less than 6, but 5 is 4 and 5 6 is 2, because 1 and 5 are the only numbers which are smaller than or equal to 6 and relatively prime to 6. So 5 is less than 6, but 5 is greater than 5 6. Means first one is not true. What about second? Second is also not true, because then 6, but hello. Hello.
Yes, sir.
Are you getting my voice?
Yes, sir. Yes, sir. Yes, sir. You are audible, sir. Okay.
Yeah, okay. Example will work for B also. So move to third. 5 is less than 7, and 5 is 4. 5 7 is, in fact, this is wrong. This is 6. 5 7 is 6. That is 5 is strictly less than 5 7. And therefore C option is also wrong. So all A, B, C are wrong. It means answer is D, none of the above. Now let us come to some difficult problems. This is the application of Chinese remainder theorem. Which of the following intervals contains an integer satisfying following three congruences? So x is congruent to 2 mod 5, x is congruent to 3 mod 7, 4 mod 11, and so on. So here GCD of 5 and 7 1, 5 and 11 is 1, 7 and 11 is 1. So they are pairwise relatively prime numbers. And therefore Chinese remainder theorem is applicable to find a common solution. Then I have to check whether that common solution belongs to this interval or this interval or this or this. So you must find common solution of this. And in the NET examination, this question was for either maybe 3 or 4 marks. So let us see the solution. In fact, I don't explain the procedure. Here, product of 5, 7, and 11 is 385. Then by using congruence, means in fact procedure to find common solution, you will get that common solution is x is equal to 2, 77 into 3 plus so on, whatever it may be. Answer is double to 92. This is the common solution. But this common solution do not belong to any interval. And you know one result, if A is congruent to B modulo n and B is congruent to C modulo n, then A is also congruent to C modulo n. That is transitivity. So try to find this number 2292 is congruent to how many numbers which belong to these intervals. So first one is 2292 is congruent to 367 modulo 385. If you add 385 to this number, you will get next number 752. If you add 385 to this, you will get next number. Now here smallest number is 401, largest is 1200. And now all these numbers, this is smaller than 400, this is smaller than 1200. So this number do not belong to any interval. Whether 752 belongs to this interval. And last one, 1137, sorry, 752 belongs to this interval. And last one belongs to this interval. So there are two intervals in which common solution of this system belong. Therefore, correct options are B and D. B and D, they are correct answers. Next, what is the last two-digit number of 7 raised to 81? But this is the application of Euler's theorem. I want to find last two-digit number. It is sufficient to find remainder when this number is divided by 100. If you divide given number by 100, you will get a remainder. And that remainder must be smaller than 100. So it must be two-digit number. So it is sufficient to find remainder when this is divided by 100. Now GCD of 7 and 100 is 1. 7 and 100 is 1. So we can use Euler's theorem. Euler's theorem is if GCD of A and N is 1, then A raised to phi n is congruent to 1 modulo n. So 7 raised to 500 is congruent to 1 modulo 100. Now what is 500? 100 is 2 square into 5 square. So according to formula, this formula, 7 raised to 2 square minus 2 raised to 1 into 5 square minus 5 raised to 1. That power become 2 multiplied by 20, that is 40. So 7 raised to 40 is congruent to 1 modulo 100. Raising this by power 2, you will get 7 raised to 80 is congruent to 1 modulo 100. But I need 7 raised to 81. So again multiply by 7 to both sides, you will get 7 raised to 81 is congruent to 7 modulo 100. So 7 is the remainder when this number is divided by 100. So whether answer is 7 or 07, we need two-digit number. So it must be 07. So if I say one answer is 7, then which will be correct? So definitely C is wrong. 07 is the correct answer. On the similar lines, you can find solution of this. What is the last digit of 7 raised to 73? We need last digit. It is sufficient to find remainder when this number is divided by 10. So you may do this yourself. This is somewhat interesting. Which of the following prime numbers satisfy the congruence A raised to 24 congruent to 6a plus 2 modulo 13? Here prime numbers are given. Without knowing any theory, you can do this problem. but it will take some time. Means put 41, value of 41 here, value of 41 here, then check whether they are congruent or not, and so on. But let us use some Fermat's theorem and congruence theorem. I will break this in two parts. First part is find the remainder when a raised to 24 is congruent to a raised to 24 is congruent to something modulo 13 for these values. And then we will come to 6a plus 2 is congruent to something modulo 13. Then we collect those congruences which match together. So first, let us see a raised to 24 is congruent to something modulo 13 for these values. Here GCD of a and 13 is 1 because a belongs to this set. So GCD of 13 and these numbers is 1. So I can use Fermat's theorem. Fermat's theorem says a raised to p minus 1 is congruent to 1 modulo p. So you will get a raised to 12 is congruent to 1 modulo 13. We need a raised to 24. So a raised to 24 is congruent to 1 modulo 13. Now this is true for all a belongs to this set. That is 41 raised to 24 congruent to 1 mod 13, 47 raised to 24 congruent to 1 mod 13, and so on. So it is sufficient to find a's for which 6a plus 2 is congruent to 1 modulo 13. All those a will be the answer. So first, take a equal to 41. Then 41 is congruent to 2 modulo 16. I need 6 into 41. So 6 into 41 plus 2 is congruent to 6 into 2 plus 2. But 6 into 2 is 12, 12 plus 2 is 14, and 14 is congruent to 1 modulo 13. So for this value of a, you will get 6a plus 2 is congruent to 1 modulo 13. It means 41 is correct option. Check whether others are correct or not. 7. Next, 47. 47 is congruent to 8 modulo 13 because 47 minus 8 is 39. 39 is divisible by 13. So multiply by 6 and add 2. It will be 6 into 8, 48 plus 2, 50, and 50 is congruent to 11 modulo 13. So this number 6a plus 2 is not congruent to 1 modulo 13. It means 47 is not the correct option. Similarly, third number. 67 is congruent to 2 modulo 13 because 67 minus 2 is 65. So multiply by 6, add 2. It is 6 into 2, 12, 12 plus 2, 14, and 14 is congruent to 1 modulo 13. Therefore, 67 is also correct option. And finally, 83 is congruent to 5 modulo 13. Multiply by 6, add 2. It will be 6 into 5, 30 plus 2, 32. 32 is congruent to 6 modulo 13. So that is not congruent to 1 modulo 13. And hence, by 1 and 3, 6a plus 2 is congruent to 1 modulo 13 for 41 and 67. Also, a raised to 24 is congruent to 1 modulo 37 for all. Therefore, both are congruent for only these two values. So this is the these are the options A and C which are correct. And C, this was the 84th problem Means it is for, I think, 4 marks. Given a natural number n greater than 1, such that n minus 1 factorial is congruent to minus 1 modulo n, then what we conclude? Whether n is a power of prime, whether n is product of distinct primes, whether n is product of three distinct primes, or whether n is a prime number. You observe that this statement is exactly the converse of Wilson's theorem. And you know that converse of Wilson's theorem is also true. So what is the Wilson's theorem? If p is a prime number, then p minus 1 factorial is congruent to minus 1 mod p. And now converse of this is, if p minus 1 factorial is congruent to minus 1 mod p, where p is greater than or equal to 2, then p is a prime number. So those who know Wilson's theorem and its converse, they can immediately answer this, and answer is n is prime number. And in fact, proof of converse of Wilson's theorem is trivial, not difficult. If n is not a prime number, then n has a prime divisor, say t, lying between 1 and n strictly. So t must divide n minus 1 factorial. Also, n divides n minus 1 factorial plus 1 because of given thing. From this, n divides n minus 1 factorial plus 1. But t is a divisor of n. So t must divide this. That is, t divides this. So by 1 and 2, t divides difference. It means t divides 1. That is not possible because t is larger than 1. And so n has to be a prime number. This is a problem, in fact, belong to number theory as well as algebra. F is a function from Z to Z4 cross Z6 defined by Fn is equal to n mod 4, n mod 6. This n mod 4 means what? This should be the remainder when that number is divided by 4. And we know elements of Z4 are 0 bar, 1 bar, 2 bar, 3 bar. Elements of Z6 are 0 bar, 1 bar up to 5 bar. So image will contain Cartesian product elements of Z4 and Z6. And they are of the type R bar, T bar, where R is the remainder when n is divided by 4 and T is the remainder when n is divided by 6. So this is our function. Fn is equal to R bar T bar. Then what we see here, whether 0 mod 4, 3 mod 6 in the image of F. So 0 mod 4, 3 mod 6 means in this language it is 0 bar 3 bar. So whether 0 bar 3 bar is element of image or not. This is the image set. Second, A mod 4, B mod 6. That is A bar, B bar is in the image of F for all even integers A and B. Now for all even integers A and B means this A bar should be either 0 bar or 2 bar as it is element of Z4. And B bar must be 0 bar, 2 bar, 4 bar as it is element of Z6. So this is the meaning of option B. Next, image of F has exactly 6 elements. And I told first that this problem also belong to algebra because of kernel F. Kernel F means all those elements of domain which are maps to zero element of codomain or identity element of codomain. So let us find first image. If you find image, you can say whether answer A is correct or not. If you find image, you can see whether B is correct or not. If you find image, you can answer the C, whether C is correct or not. And for D, you must find separately kernel F. So first we will find image F. Image F is set of integers which are congruent to R mod 4 and T mod 6, where R and T are the numbers respectively 0, 1, 2, 4 and T 0, 1, 2, 4, 5. So image will contain what is the image of 0? That is 0 is congruent to 0 mod 4, 0 is congruent to 3 bar, 3 bar, F4. F4 means 4 is congruent to 0 modulo 4 and 4 is congruent to 4 modulo 6. So image of 4 is 0 bar and 4 bar. And similarly, you can check F5 is 1 bar, 5 bar, F6 is 2 bar, 0 bar, F7 is 3 bar, 1 bar, F8 is 0 bar, 8 bar, 2 bar, F9 1 bar, 3 bar, F10 2 bar, 4 bar, F11 3 bar, 5 bar, and F12. What will be F12? 12 is congruent to 0 mod 4. 12 is congruent to 0 mod 6. So we come back to 0 bar, 0 bar. That is F0 is F12, F1 is F13, F2 is F14, and so on. F0 is F12, F12 is same as F24, F24 is same as F36, and so on. So these are the only image elements. So this set is 0 bar, 0 bar, 1 bar, 1 bar, up to 3 bar, 5 bar. And observe that this set contains 12 elements. So image F contains 12 elements. It means C is wrong answer. C is not correct. Whether 0 bar, 3 bar is in the image, check here. 0 bar, 3 bar. No, 0 bar, 3 bar is not an element of image. So option A is also wrong. What is option B? A bar, B bar, where A and B are even. So check whether 0 bar, 0 bar means these elements. 0 bar, 0 bar, 0 bar, 2 bar, 0 bar, 4 bar, 2 bar, 0 bar, 2 bar, 2 bar, 2 bar, 4 bar are elements of image or not. And you see that all those are in the image. So option B is correct. This set is a subset of image. Now how will you find kernel? Kernel is the set of all integers which are congruent to identity element of Z4 cross Z6 with respect to addition modulo 4 cross addition modulo 6. And that identity element is nothing but 0, 0. So all n for which 4 divides n, comma 6 divides n. Now 4 divides n, 6 divides n, it means LCM of 4 and 6 must divide n. So all numbers which are divisible by 12. So this set is nothing but 12Z. And hence our D option is 24Z. So it is also wrong because kernel F is 12Z. So correct option is only B. And therefore, if you find image set, you will get the answer of this. And I think I stop here. If any questions from audience, I welcome all those questions.
Thank you, sir. Now it's a session for question and answer. If any participants have any questions, please ask to sir. Looks like there is no question.
Okay.
Thank you, sir. It was really very interesting to learn number theory, and this helps students to confident about the number theory. Thank you so much, sir.
Okay, thank you, madam.
Okay, now we will have a short break of half hour. After that, we'll continue our third and fourth session. Our third session will be start at 2:30 p.m. Thank you. Thank you, sir.
Okay, thank you, madam.
चालू आहे 5 वाजेपर्यंत आहे ते. आता ब्रेक आहे मध्ये 2 ते 2:30चा ब्रेक आहे. 10 वाजता इनॉग्रेशन त्यांचं दिदीला आणि त्यांचा टाइम टेबल दिलाय.
Okay. Here the first question is, which of the following statements is false? Here C is a C vector space, and for any two scalars alpha beta, alpha dot 1 plus beta dot I, this linear combination is 0 if and only if both the scalars are 0. Then second is M is a set of all continuous functions defined on closed interval 0, 1, which has 1 by 2 as a root. Each subspace of the real vector space C01. C01 is the set of all continuous functions defined on closed interval 0, 1 to set of real numbers. So this is a vector space over a set of real numbers. And third option is V as F vector space, then alpha x is 0 where alpha is scalar and x is a vector from V. Alpha x is 0 if you know leave, alpha is 0 or x is 0. And fourth option is the class of all polynomials with real coefficients is a real vector space. Means polynomials which are defined on set of real numbers, field of real numbers, and it is a R vector space. So here we have to choose a false statement among these. So see here, the option D is always true, that addition of two polynomials is the operation and scalar multiplication for polynomials is the multiplication operation, and it always forms a real vector space. So option C is also a regular property in vector space. Either alpha is 0, then alpha x is 0, and we can easily show the direct part also. If alpha is non-zero, then we can pre-multiply on both sides by alpha inverse and you will get x is 0. Okay? So this is always a property of vector space. What about this A and B? So we have to see here, if you observe this first one, most of the student will think that this alpha 1 plus beta I is 0. So alpha is 0 and beta is 0 by comparing their real and imaginary coefficients. Okay. And converse part is trivial. If alpha beta both are 0, then this is true. But this is not true here. Why? See, if I take this field is R, if I take here field, instead of the set of complex numbers, we take set of real numbers, then we can compare their real and imaginary part on both sides and you can get there. This is true. But here the field is set of complex numbers. So we can observe, if I take alpha as I and beta as -1, then this linear combination is 0, but none of them is 0. So this is not true. What about this B? Whether this EM is a space of set of all this C01, vector space of C01. So see here, a mapping from C01 to R by this T of F equal to F of 1 by 2. Then this M is nothing but the kernel of this linear transformation. This is the linear transformation. Most of the students, if you studied algebra, advanced algebra in MSc level, then you can observe this type of function is known as evaluation function, and this is always a linear transformation. And here this M is nothing but the kernel of this T, and we know that kernel is always a subspace. So B is also true. So which of the statement is false among this? So statement A is the false statement. So option A is correct. If I consider R cube as R vector space, then which of the following is not a subspace of R cube? So this set A is set of all 3 tuples satisfying these linear equations. This is the set of all points satisfying x greater than equal to 0 and y greater than equal to 0. And third is this sets. So whenever such examples are given and asked to verify about subspace, then you have to remember that all those solutions, these are nothing but what? The solution set for this equation, simultaneous, homogeneous linear equations. So remember always that the set of solution set of homogeneous linear equation is always a subspace of given vector space. This R cube as R vector space. This note is very important to solve this type of example. No need to check any addition or scalar multiplicative property. You have to check whether these are simultaneous equations, homogeneous equations. Okay, if all that equations are simultaneous, homogeneous, linear equations, then obviously the solution set is always the subspace. So this is subspace, C is subspace, D is subspace. What about this B? So see here, for B, if I take -1 from R and 1, 1, 1 from this given set, if I denote it by W, then -1 into this 1, 1, 1 gives, that scalar multiplication gives -1, -1, -1, and it is not an element of W, because what is condition? X and Y both are greater than or equal to 0 here. These are negative, so not belongs to W, and hence this B is not a subspace. Here these four vectors are given, and these two sets are given, and we want to check whether this set X is linearly independent in R raised to 4. Similarly, Y is linearly independent in R raised to 4 or not. So whenever such a question is asked, then you have to remember that you have to use row echelon form to check whether the given set of vectors is any given set of vectors in R raised to 4 or polynomial vector space. You can easily check by using row echelon form. See here. For X, we will check whether it is linearly independent or not. So what we have to do, write this X1 as first row, this X2 as second row, and we want X4 there in X. So write this X4 as third row, and convert this matrix in row echelon form by using row operations. So simply you have to operate there R2 minus R1. So by performing this operation, you will get this, and actually no need to go for further, because you can observe here these two are not multiple of each other. Second row and third row, these are not multiple of each other. Okay, so no need to go further, means you will not get here 0 row. So all vectors are there, and hence we can say the X given set X is linearly independent. If I get here this is multiple of second row, then I will say that the given set is linearly dependent. Okay, but here all are linearly independent, means after converting this into row echelon form, no 0 row is occurring, so we can have here X is linearly independent. Similarly, we can go for the Y, and here you can also observe the Y also linearly independent. Okay, so correct option is C. Both X and Y are linearly independent. Same technique you can use also for the polynomial vector space, means a polynomial vector space of at most n degree over reals, like that. That sets are also you can verify whether it is linearly dependent or independent. This next question is application of extension theorem. See here, V be a finite dimensional vector space over field K. Here T is linearly independent set, B is the basis for V, and S is a generating set. Okay. So most of the time we always apply whatever theory we have studied, like extension theorem here. We know that what is the extension theorem in vector spaces? Every linearly independent set can be extended to its basis for finite dimensional vector space. Okay. So instead of applying that theory, whatever you have studied, you can we find a counter example for such type of options? So see here, sometimes that is more suitable instead of applying the theory whatever we have studied. See here, what we want, this is a general statement about the finite dimensional vector space. So can we find a finite dimensional some vector space so that this D fails, C fails, B fails, or A fails? Okay, so see here, I will take here set up real numbers as R vector space. R as R vector space. Then we know that the dimension of R as R vector space is 1. Any non-zero element in that R is a basis. Okay. So I will take singleton 1. Then singleton 1 is the basis. See here. Singleton 1 is the basis for R as R vector space. And therefore, number of element in basis is 1, means cardinality of B is here 1. Number of elements, basis means linearly independent and generating set, spanning set. Okay. So this is linearly independent. So number of element in T is also 1. And this is also a generating set for this vector space, finite dimensional. So number of element in S is also 1. So we have there an example which shows that this is not true, because strict inequality always hold. This is the statement. So that is not possible. We have found an example here. So equality hold. So this is wrong. Similarly, this is wrong and this is also wrong. So what is the correct option? This A is the correct option, because this is what, if we think about the extension theorem, this is the extension theorem. If V is a finite dimensional F vector space, then every linearly independent set can be extended to its basis. Means number of element in linearly independent set is always less than or equal to number of element in basis. Also, there is one result theorem in vector spaces linear algebra. Every minimal generating set of a finite dimensional F vector space forms a basis for V. Means if we find in generating set those, if we remove those elements which are linear combination of remaining elements, then you will get the minimal generating set, and that minimal generating set forms a basis. Means number of element in basis are always less than or equal to number of element in generating set. So combining these both, you will get this A option is correct. So next. This next question is the application of dimension of quotient space. Means V is a dimension, V is a finite dimensional F vector space. Then dimension of V upon W is dimension of V minus dimension of W. This theorem is that well-known theorem in vector spaces about dimension of quotient space. And here, what is W? W is subspace of R raised to 4, which is generated by these three vectors. And we want to find the dimension of this quotient space. Whether dimension of this quotient space is 1, 2, 3, or 4. So we know the dimension for quotient spaces, that is dimension of R raised to 4 minus dimension of W. Dimension of R raised to 4 is 4 or R. We want to find the dimension of W. Okay. So for that, if you observe, we want to have here this three elements are linearly independent or not. So use again the same row echelon form technique, and it is a generating set for W. We have to check only the linearly independent set. Okay. And for linearly independent, again we take this as first vector, this as second row vector, and this as third row vector. And after performing this operation, we have converted it into echelon form. Here you can observe that this third row is a multiple of second row. So this set is not linearly independent, and only linearly independent rows are here, first and second, 2. So dimension of this W is 2, generating set, and there are only 2 vectors which are linearly independent among these 3. So dimension of W is 2, and we know this theorem, dimension of R raised to 4 by W is dimension of R raised to 4 minus dimension of W, and this will gives you 4 minus this 2, answer is 2. So here the correct option is B. This is also a example on dimension of addition of two subspaces. So here V is a finite dimensional K vector space. Then W and U are subspaces of V. Then which of the following statement is correct? So again here we can we find here a counter example which fails this, or this. So before that, I have to mention the result which is well known in vector spaces for dimension of sum of two subspaces. This is that theorem. Dimension of W plus U is nothing but dimension of W plus dimension of U minus dimension of their intersection. So see here, I want to go for we can find the counter example also for this A, B and D also. So before that, I want to go for this. Dimension of W plus U equal to dimension of U, dimension of W plus dimension of U. So this is true. So from this statement, we can have dimension of W intersection U is singleton 0. So dimension of this intersection is singleton 0 means that intersection is a singleton space 0. And now we have intersection is singleton 0. We can write W plus U equal to W plus U. So if you use the definition of direct sum of subspaces, then you will get here W plus U is direct sum of W and U. So here option C is correct. Okay, this is true if and only this is true. And also we can give an example for this. If I take here W as, for first, W as R square as R vector space. In R square as R vector space, take W as R square, take U as R square, then R square plus R square is itself, because addition is closed in that. So dimension of left hand side, that is R square, that is 2, but dimension of R square, W we are taking R square, U is taking R square. So 2 plus 2, 4. So this is not true always. Similarly, we can give example for this B and D also. Okay. So simply if you want to give the example, take here the non-zero intersection is not equal to 0 example. Okay. So here the correct option is C. Now many times the question about dimension of vector space of matrices is asked in NET exam as well as in SET exam. Various type of examples are there on dimension of vector space of matrices. So this is one of them. The vector space V is set up all n by n real matrices in which this condition hold. Summation Aij equal to 0 for every I. Means here you can observe, set up all those matrices in which addition of all, this is what? If I take I equal to 1, then this is nothing but sum of all elements in first row. So addition of all entries in first row is 0. This is the condition. For first row is 0, for second row is 0, for third row is 0, for every row is 0. Sum is 0. So this condition is given on that matrices. And we want to find dimension of this vector space over R. So here, for example, if I from this condition we can write the first entry AI1 as linear combination of remaining element. So I have replaced this A11 element in terms of the remaining 3. This A21 entry in terms of these 3. This A31 entry in terms of this 3 because of this given condition. So see here how many entries we require to write this type of matrix. Dimension is nothing but what? Find how many non-zero entries we require to write this kind of matrices. That is nothing but dimension of this type of vector space. So how many elements are required, entries are required? See here. This entry we can write in terms of these three. So leave this. These three entries are useful to write this entry. So leave this, similarly this, and count remaining entries. So this is what? The total number of entries minus number of entries in first column. Okay. Total number of entries are 16 minus this 4, 12. Okay. So in n by n matrices, what will be the dimension? Total number of entries are n square. And how many entries we are neglecting? N. One column we are neglecting. So n entries we are neglecting. So the dimension is there n square minus n. So for such type of example, you have to count only the non-zero entries which are required to write such type of matrix. Minimum number. That is also more important. The minimum number of non-zero entries required to write A is n square minus n, and hence the dimension of this vector space is n square minus n, and therefore the correct option is A. Now this is another similar type of example where we have Hn is the space of all n by n matrices of this kind, satisfying Aij equal to ARS. That entry satisfies this property for all Ij and Rs belongs to this. Then dimension of Hn we want to find over R. So see here again, if I write this, instead of taking their n, you can take their 2, 3, and a particular example, you can easily get the answer. Okay. So see here, if I write that matrix A, which satisfies this property. What is that property? Sum of suffixes is same, then the elements are same, like this. See here, 1, 2 and 2, 1 entry. These are same. 1, 3, 3, 1. These are same. 1, 3, 2, 2 and 3, 1. These are same because their suffixes are same. Addition of suffixes is same. 1, 3, 4, 2, 2, 4 and 3, 1, 4. Next, this 1, 4, 5, 2, 3, 5, 3, 2, 5 and 4, 1, 5. See the sum of suffixes. Then this off diagonal, then this below off diagonal, this and this. So how many entries we required here for write this type of matrix? So see here, one entry, sorry. This A44 is one entry. A31 and A43 is same. So this another entry, this another entry, this entry, this entry, this entry, and this entry. So what you have to do? You have to count only these elements: A11, A12, A13, A14, 24, 34, and 44. Because these elements are same, these elements are same, these elements are same, like this. So how many elements, minimum number of elements are required to write this type of matrices? 1, 2, 3, 4, 5, 6, 7, 7. That is what? Number of element in rows plus number of element in this first column, first row, and this last column, and minus 1. It is repeated. So what for n? It is n plus n minus 1. So dimension is there, 2n minus 1. So answer D is correct. In next, this is skew symmetric matrices, vector space of all this type of matrices. So again, you have to count only the number of non-zero, minimum number of non-zero entries. Okay, and you will get the answer. Okay, so we know that for skew symmetric matrices, diagonal entries are 0. Okay, Diagonal entries are 0, and this can be written in terms of this one. This can be written in terms of this one, negative of this, like this. So how many entries we required here? 1, this 2, this 3. So 1 plus 2 plus 3. Order of this matrix is 4 by 4. So 1 plus 2 plus 3 means less than 4. 1 less than 4. So likewise, for this type of vector spaces, minimum number of non-zero entries required to write this type of matrices is 1 plus 2 plus 3 up to plus n minus 1. And this sum is this. So the correct option is here D. Symmetric complex matrices. So here, symmetric complex matrices. So how many entries we require? So below diagonal, you can exclude the entries. So you have to count the, it is also, you have to remember that the vector space is over R. Okay. So how many entries we require to write this complex number? 2. This 2, this 2. On the diagonal and above the diagonal entries you have to count. Okay. Actually, this is 1 plus 2 plus 3 plus 4 into 2. So for n, you have to count this number. And that is nothing but n square plus n. So option is here, C. Okay. Now, this is the question about the matrix of linear transformation. And this is the example on the well-known theorem in linear vector spaces about matrix of linear transformation. So matrix of linear transformation. That is what? Whenever we have the domain vector space is finite dimensional and you are choosing some basis or linearly independent set from that, then it can be uniquely mapped to some vectors in R3. And that mapping is always unique. So this D is wrong. Such type of linear transformation always exists and it is unique. So we have to check whether this is the formula for that linear transformation or this or this. So how? You have to simply find that T of alpha 1. So T of alpha 1 means T of 1, 2. If I find here T of 1, 2, then put here x is equal to 1 and y equal to 2. So first entry you can observe here, that is 3 by 2. And you will have, this is not equal to T of alpha 1 should be equal to T of alpha 1 equal to beta 1. So it is not equal to 3 by 2 is not equal to 3. So this is not the correct option. Similarly, B is not a correct option. If you go for third option, this is always wrong because of this theorem. Third option, then you can observe, you will get T of alpha 1 is beta 1, T of alpha 2 is beta 2. And hence this C is the correct option. And such type of linear transformation always exists, and that follows from this theorem. Okay. Next is about if F is a linear map from U to V, then the linearly independent set is mapped to linearly independent set under this here, if and only if. So this is actually a well-known theorem in vector spaces about linear transformation dimension. And here the correct option is B. T is linear operator, and here dimension of kernel T is greater than 0. Then which of the following is correct? So see here, dimension of kernel T is greater than 0 means kernel T is a non-zero subspace. Okay. So here we know that T is on to if and only if T is 1, 1 and T is invertible. That is a well-known theorem. And here dimension of kernel T is greater than 0 implies kernel T is non-singular. Therefore, there exists some non-zero vector satisfying this, means 0 is the eigenvalue. So Here A is the correct option. Why B is not correct? So you can observe that from this and by theorem this. For C, we can find out some linear transformation which face this having dimension. Here you can observe. Kernel T has dimension 1 greater than 0. T square, T is idempotent, so it is not nilpotent because it is non-zero linear transformation. Okay, and similarly we can have from this theorem, this is option D is also not there. Here also we can have this question about linear transformation which maps the standard basis to these vectors. So this type of linear transformation always exists, that already we know. So it is linear. What about idempotent? Kernel T is non-zero. Kernel T is non-zero here because this E1 has mapped to 0. So we have there kernel T is not equal to singleton 0. So option C is wrong. What about nilpotent and idempotent? So see here, it is not idempotent because T square of E2 is not equal to T of E2. Here you can simply calculate and observe T square is not T. What about nilpotent? This degree of potency for this type of T is N. You can observe that from a particular example. You can continue that for 4, 5, and 6 up to N. Okay. So now in this example is based on rank nullity theorem. Kernel T and range of T is given here, that is equal in every option. Okay, and we have to find out whether such type of linear non-zero linear transformation exists satisfying this or not exists for RS25 and RS26. So see here, using rank nullity theorem, we can observe dimension of V is rank of T and plus nullity of T. Here range and kernel T is same in every option. So from that we can have rank of T and nullity of T is same. And if you replace that here, you will get dimension of V is equal to 2 times rank of T. So for first option, if we assume this type of T exists, then using this one, we can have dimension of RS25. Here V is RS25 equal to 2 times rank of T. But this is not 2 because 2 divide 5, that is impossible. So such type of linear transformation does not exist. So A is wrong, so B is correct. What about 6, RS to 6? So we can have there a possibility for such type of existence of T. And what will be that? This is that linear transformation. We have given here a range of T is this space having rank 3. And if we find the kernel, then it will be this set which is equal to range of T. So such type of linear transformation exists. So option C is correct. Option B is correct here. This is about matrix of linear transformation. That is the usual question. And remember that whenever dimension of codomain is here 2 multiplied by dimension of domain, that is 3. So matrix of linear transformation is here a 2 by 3 matrix. So option B or C is correct. And if you simply map this 1, 0, 0 standard basis first element, if you find, then you will have T of 1, 0, 0 is this, and it can be written in terms of the standard basis for R square, and you can have these coefficients are 1, 0. So observe only first column 1, 0. So option B is correct here. No need to go for the remaining elements of this R cube. Okay. Similarly, we can do for the same thing here. The reflection matrix. So reflection matrix means about origin. That definition is enough to have here the answer. So option C is correct. This is the question depending on that characteristic polynomial. Simply you have to compute that characteristic polynomial. Instead of computing that all the that characteristic polynomial, simply observing you can write the answer for this. If you observe the first matrix, Pax is the characteristic polynomial of A, and we have to check whether the difference is constant or not. So if you observe the entries from this, the eigenvalues for this matrix is sum is 6. So 6 is one eigenvalue, trace is there 7, so another eigenvalue is 1. So 1 and 6 are the eigenvalues. You have to observe only that what eigenvalues, and if you compute it, so you can get the answer. If you find a trace using this trace of A 1 and 6, trace of A inverse will be 1 upon 1 plus 1 upon 6, and that difference is never 0, means 7 and 7 by 6 is not 0, so this never be a constant. Similarly, for second matrix is same answer, so this is not constant. For this matrix, again if you compute the trace of this and trace of A inverse, determinant of this is 1, 9 minus 8, 1. So you will have the trace of A and trace of A inverse is same, and you will get the difference is 0. Okay. So similarly, this D has difference is 0. So constant are for C and D. You have to simply calculate their determinant and eigenvalues or trace. You can get the answer. This is a question from set examination that was asked for R square as R vector space, but that question was wrong, because if I take R square as R vector space, this type of matrix do not have an eigenvalue in R. So if we change this R square by C square as R vector space, then the answer will be D. Simply calculate the characteristic polynomial, that is x square plus 1. Characteristic polynomial has roots I and minus I. So over C it has answer, but over this R square as R vector space, it do not have an answer. And this is the similar question. This is the question related to the well-known results from vector spaces. And that theorems are this one. There does not exist AB belongs to MNC, satisfying AB minus BA is identity matrix. Over C it do not exist, so over R obviously it is not possible. Second is also a result from this theorem. Both are diagonalizable together, means A is diagonalizable if and only B is diagonalizable. So here this is also correct. This is wrong, this is correct. This, we can't say anything about the minimum polynomial, so this is wrong. But we know about the answer for this last, D. This type of matrices always have same eigenvalues in R. Okay, so here the options B and D are correct. In this type of matrices, to find minimum polynomial, if you observe this matrix, it is of the type, you can write this one entry as a submatrix, this 2 by 2 matrix as a submatrix, and this as C and this as D. So eigenvalues of this matrix are 1. If you observe this submatrix, then identify their sum of these two entries, that is 2, this is 2. So eigenvalue for this submatrix is 2, one eigenvalue is 2, and addition of trace is 3. So 3 minus 2, that is 1. So eigenvalues for this matrix are 1, 1 and 2. So this is the characteristic polynomial of this matrix, lambda minus 1 square, lambda minus 2. So to find minimum polynomial, there are only two possibilities, either C is possibility or B is possibility. So you have to compute only this product of two matrices, replacing that lambda by A and this one as 1 into I, identity matrix, and compute this. If it is 0 for this, then this C is the minimum polynomial of A. Okay, so option C is correct. To find Jordan form of this type of matrices having this as minimum polynomial as well as characteristic polynomial. So order of this matrix is 4 by 4, and here we have to write a block respective this first eigenvalue by writing that 1 1 1. Here you can observe in C 1 1 1 to the diagonal, super diagonal entries are 1. So it is a 3 by 3 matrix for this first eigenvalue, and for second eigenvalue it is 4. So correct option is always here this type of matrix. C is the correct option. This is similar type of example. Here, if A is a matrix having characteristic polynomial like this and minimum polynomial like this, then which of the following is not true? So simply you can calculate trace from this characteristic polynomial, that is 2 into 1 into 3, that is trace. So 2 plus 2 plus 1 plus 3. So you have to take addition of these values 2, 2, 1 and 3. So 8, trace is correct. Then we have to find determinant. So take product 2, 2, 1 and 3, that is 12. So this is also correct. A is diagonalizable over R. See here the minimum polynomial has this form. So it is product of distinct linear factors, and hence we have the matrix is always diagonalizable over R. So option D is correct. So D is the correct option. This is the application of the theorem on diagonalizable matrices. If whenever we have such type of characteristic polynomial is given for the linear transformation and T is diagonalizable, then the minimum polynomial is product of distinct linear factors. So these two possibilities are not correct. What about dimension of kernel of T minus 5y? So whatever power is there in characteristic polynomial, that is nothing but the dimension for null space of T minus 5y. So option B is correct. This is about diagonalizable matrices, and here you can easily observe if all eigenvalues are distinct, then it is diagonalizable, otherwise not. Okay, otherwise again we have some another criteria. So see here all are distinct, so this is diagonalizable. Here repeating, so we will think about it. These are distinct, so it is diagonalizable. This is diagonalizable. One option is correct, so B is the correct option. Similarly, this is the another example on diagonalizable. These are the this is example on the regular properties of the orthogonal matrices, Hermitian matrices, and unitary matrices. Okay, there is nothing to do them and that. Quadratic form for symmetric matrices, if you multiply xy, a row vector to this, to a column vector same xy, then you will have the answer is D. So I think I have to stop here. If anybody have any query about this, then one can ask this.
Hello.
Thank you, sir. Yes, sir.
Good afternoon, sir.
Good afternoon.
Sir, I am Sir Shoaib Akhtar from Adarsh Mahavidyalaya, Damangaon Railway.
Okay.
Sir, I am a CSIR NET set aspirant. First of all, thank you, sir. Sir, you are taking more than 50 questions on linear algebra, and I hope this is very helpful for our SET exam held on 27 December 2020.
Okay.
Sir, I have a doubt in a question on page number 42. Can I see?
42.
Yes, yes.
Yes.
No, sir.
42.
I think, sir, 44. Next page, sir, please.
Huh?
Next page, sir. No,
This?
sir. No, sir. Sir, please. Page. I think page number 41.
41. Okay.
No, sir. This is a question related to the vector space. In which, in this question, yes, sir. This question.
This question.
Yes, sir. Sir, here R2 over C2.
No. R2 over C2, no. There is another. Don't think about this C square.
Yes, sir.
No.
This,
there is a vector
C
space. R square as a R vector space.
Yes.
R square as a R vector space. But if you take R square, this question was asked in SET examination of August 2011, question number 40. And that question was asked for R square as R vector space. But if you take R square as R vector space, then this type of matrix has characteristic polynomial this, and it has roots I and minus I, and I and minus I do not belong to reals. So if we take R square as R vector space, then it will not have eigenvalues, that I have told. But if you replace this R square by C square as C vector space, then it has an answer that I have said. Okay.
But this C square is not a field, sir. That means
C square.
Yes.
No. C square is not field, but C square is a abelian group. It is a abelian group under addition, and we are taking C square as vector space over field of complex number C.
Okay, sir.
Okay.
Yes.
C square I am taking as a abelian group under usual addition of order pair complex number, and I am taking field as C, complex number field.
Yes, sir. Okay, sir. Thank you, sir.
I have told that this R square, don't take R square. C square is a C vector space, then it has an answer. Otherwise, it will not have an answer. That I have told. Okay.
Thank you, sir.
Okay. Anybody else?
Any other participants have any questions? Looks like sir answered all your questions. Thank you so much, sir.
Thank you, ma'am.
Thank you, sir, for your insightful presentation. And again, thank you for sharing your time and knowledge with us, sir.
Thank you, ma'am.
Thank you, sir. Now, we are moving towards session 4. May I now request our resource person for the session 4, Dr. Uday Thul, sir, to esteem our audience.
Thank you. I think I'm audible to you.
Yes, sir. Yes, sir.
So, good afternoon, friends. I welcome you all in this fourth session of university level workshop on NetSet guidance in mathematics, organized by the Department of Mathematics, Sant Gadge Baba Amravati University, Amravati, in collaboration with RDIK and KD College, Vadnera, Adarsh Science JB Arts and Birla Commerce Mahavidyalay, Dhamangar Railway, Dr. R.G. Rathod Arts and Science College, Murtizapur District, Akola, on this auspicious occasion of 133rd birth anniversary of India's legendary mathematician Srinivasa Ramanujan. Friends, due to some technical difficulties, I am unable to present PPT of my lecture. So I will only try to present my lecture. I hope organizers and you people will excuse me for this. Before I begin my lecture, I go down to world famous Indian linear mathematician Srinivasa Ramanujan. We celebrate his birthday as a National Mathematics Day to commemorate the wonderful contributions and thorough devotions of Srinivasa Ramanujan in mathematics. Trivar Vandan for his unique, wonderful work and for his inspiring contributions in mathematics. I I have divided my lecture in 4 parts. The first part is brief introduction of syllabus of NET and SET and the paper pattern. Second part, some basic concepts in algebra, number theory. Third part, assignments. I'm trying to give you some assignments, not more, only 2 assignments. And fourth one is a motivational conclusion. Now, first part, CSIR UGC NET is a single paper exam of 200 marks, having multiple choice questions. The paper is divided into 3 parts, A, B, and C. Part A carries 20 questions on general science, quantitative reasoning, and analysis and research aptitude. Among these 20 questions, you have to answer any 15. Each question is of 2 marks. You can score maximum 30 marks in part A. Part B, it contains 40 marks, 40 MCQs from the given syllabus. You should have to answer any 25 questions. Each question is of 3 marks. You can score maximum 75 marks in part B. But be aware, both for part A and B, there is a negative marking at the rate of 25% for each wrong answer. Part C, this part contains 60 questions. The questions in this part shall have multiple correct options, and credit in a question shall be given only on identification of all the correct options. You have to answer any 20 questions, each of 4.75 marks. You can score maximum 95 marks from part C. The syllabus is divided into 4 units and is available on the net. So I will not take time in discussion with the syllabus of NET. Unlike NET exam, SET is an objective type exam. Consists of 2 papers held on same day in 2 sessions without breaks. Part 1 carry 50 compulsory questions, each of 2 marks. You should have to solve it in 1 hour. Paper 2 carry 100 compulsory questions, each of 2 marks, and you should have to solve in 2 hours. There will be no negative marking. There will be no negative marking. This is my part 1, part A, or one of my part of my lecture. Now I'm moving to part 2 of my lecture about some basic concepts. As you are aware that algebra is one of the important topic of NET and SET exam syllabus. I will discuss some basic concepts. The first, actually, you may find nothing in this concept, but I would like to, but I think I should have to share my ideas of this concept. Binary operation on a set. The first requirement of this concept is a non-empty set. Non-empty set. Now, why non-empty set? You should have to think. Actually, while studying the subject, we should have to ask ourselves such questions. Unless and until we get satisfactory answer, we should not have to leave it and go ahead. So here I have posed one question in your mind: why the set is non-empty? While defining binary operation, why the uh, requirement of the set is non-empty? Now next, binary operation on set G means suppose G is a non-empty set. Then binary operation on a set G is a mapping, say F, small f, defined on, which is defined on the cross product of set G cross G to G. That is a mapping F G cross G to G is a binary operation, or is called a binary operation on set G. Here we observe that image of each order pair AB, image of each order pair AB, A small a comma small b, order pair. Here A and B are the elements of G. Under rule F, under mapping F, is an element of G, is an element of G. That is, whenever AB belongs to G, then there exists another element C in G such that F of order pair AB equals to C. Here it seems that two elements A and B of G are processed by certain rule to get element C. Sometimes we denote this mapping by star. Thus, star requires two operands to operate. Hence is called as binary operator or binary operation. Therefore, like usual mathematical operators, we write or we denote star of order pair AB as A star B. Okay, A star B. Therefore, if A star B belongs to G, if suppose A star B belongs to G, for all AB belongs to G, then star is a binary operation on G. Then star is a binary operation on G. Some authors term this as a closure law or closure property. But explicitly, if we have mentioned that star is a binary operation on a set G, then G is necessarily closed under star. Then G is necessarily closed under star. Hence, while defining the group G, there is no need to write the first exam as G is closed with closed under star. So now I'm moving to the definition of group. A non-empty set G along with a binary operation star on G is called a group if the binary operation star is associative. That is, if suppose A, B, C are any three elements of G, then A star in bracket B star C bracket close, if it happens that it is equals to in bracket A star B bracket close star C, then we say that star is associative or associativity holds with respect to star. So first exam is of associativity, means binary operation is associative. The second exam says that identity element E exists in G with respect to star. Here I have explicitly added the word with respect to star. Here identity depends on the binary operation. That's why I have mentioned it as a with respect to star. I hope you are well aware about the identity element. An element E is called as identity element of set G with respect to star if A star E equals to E star A equals to A for all A belongs to G. This is the kind of definition actually. It is a combination of left identity, right identity, etc. etc. I'm not discussing that part. And the third property, third one, every element of G possesses inverse with respect to star. Every element of G possesses inverse with respect to star. Now, what element is called as an inverse? An element B of group G is called as inverse of A if A star B is equals to B star A is equals to E. Okay, and we denote inverse of A by A superscript -1. We denote inverse of an element A by A superscript -1. I'm not saying A raised to the power -1. Okay, note it carefully. A superscript -1. While reading, we read it as A inverse, but it does not mean that 1 by A. It does not mean that 1 by A. So it is inverse element of A, and the meaning of that is A star A inverse is equals to identity. So in addition, if star is commutative, that is A star B is equals to B star A for all A B belongs to G. Then we say that star commits or star is commutative operation. Then we call that group G is a abelian group. Otherwise non-abelian group. Now, particularly abelian group plays a very important role in algebra, or there are so many applications of abelian group. So here I'm not concentrating on non-abelian group. If A is an element of a group G, then for any integer n, so any integer means n may be positive, negative, maybe 0. So if n is negative, if n is positive integer, then A superscript n. I'm not pronouncing it as A raised to n. You can read it as, but the meaning is not exactly that. A superscript n is equals to A star A, how many times? N times. A star A, how many times? N times. And if suppose if n is negative, then A superscript n is equals to A inverse star, how many times? Minus n times. Okay. And if suppose n is 0, then A superscript n is equals to A superscript 0 is equals to E, identity element of G with respect to star. If every element of G is of the form A superscript n for some integer n. Okay, note it carefully. If every element of G is of the form A superscript n for some integer n, and for some integer A, and for some fixed integer for some fixed element A in G, then G is called a cyclic group. Generated by A. A is called as the generator of cyclic group G. Over here, there is one result. Cyclic group is necessarily abelian group, but converse may not be true. This can be easily proved by producing counter example. Here, we cannot prove this result directly, but by some counter example, we can show that abelian group is not necessarily cyclic. This every cyclic group is abelian group, but every abelian group may not be cyclic. You can take this as an assignment. Here, I would like to uh, discuss very important example of an abelian group with you. You note this example. This example is very important and plus very tricky rule, okay, and interesting one. Let G be a set of 2 by 2 matrices of the form first row A, second row A, means all 4 elements are same A, where A is non-zero real number, where A is non-zero real number. Then this will form a abelian group. Then G will form a abelian group with respect to usual matrices multiplication as a binary operation. Okay, then this set of 2 by 2 matrices G will form an abelian group with respect to matrices, usual matrices multiplication as a binary operation, as a binary operation. But at a glance, one may say that it is impossible, isn't it? Since we know that in general, matrices multiplication is non-commutative, and even identity element with respect to usual matrices multiplication is with respect to with respect to 2 by 2 usual 2 by 2 matrices multiplication, with respect to 2 by 2 matrices multiplication is 1 0 0 1, and which is not equals to the element A matrix 2 by 2 matrix A for any real number A belongs to R. So it seems that particularly at a glance it says in that we the identity element is not there in G, and the matrices multiplication is not necessarily commutative. Even then, I have claimed that G is a abelian group. G is a abelian group. So this is one more assignment. You work out this and show that G is an abelian group with respect to binary operation of matrices multiplication, usual matrices multiplication. Again, I'm making one additional comment. Moreover, this can be extended to form a field. Moreover, this can be extended to form a field by introducing 2 by 2 null matrix, by introducing 2 by 2 null matrix in G. So again, you can work out this this problem, whether this G is whether this G is a field will become filled or not with respect to usual addition and usual multiplication of 2 by 2 matrices. You check it. We have learned. Now I'm shifting my this topic to certain another topic of the algebra, or even you can relate this with number theory. We have learned congruence modulo n relation. Okay, that this congruence modulo n relation is an equivalence relation on the set of integers, and we know that every equivalence relation partition the set into disjoint equivalence classes. Thus we have, if suppose n is a integer greater than 1, if suppose n is integer greater than 1, then I'm considering here module number n as greater than 1. If you have considered n is equals to 1, then there is as such no meaning. It is equivalent to set of integers z. So therefore, the requirement of n is greater than 1. So here we observe that if suppose n is greater than 1, then z set of integer is equals to union of 0 bar, 1 bar, 2 bar, etc. Union of n minus 1 bar. Here a bar denotes the equivalence class of A, or equivalence class generated by A, and it is set of all integers x such that x is congruent with A modulo n. X is congruent with A modulo n. Now over here, I hope that you are aware about this relation. A is congruent with B modulo number m or n. It means that m divides the difference A minus B or B minus A. Okay, so a bar means what? Set of all integers x such that x is congruent with A modulo n. We denote the set of equivalence classes of congruent modulo number n as Zn. Some of the author has used Z suffix n. Some of the author has used Z slash n. Okay, choice is yours. Okay, the meaning you should have to know. You should have to know. So Zn, I'm using Z suffix n. Z suffix n is equals to, or we will read it as Zn. Zn is equals to the set of 0 bar, 1 bar, etc., n minus 1 bar. Sometimes without bars also, even we can write Zn is equals to 0, 1, 2, n. But over here, you should not have to confuse yourself. Zero, it doesn't, it is not a single zero, but it is a set of all elements which are congruent with 0 modulo n. Okay, so we have learned that Zn form an, again also we have learned that Zn forms an abelian group with respect to addition defined by, we suppose a bar and b bar be any two elements of Zn, then a bar plus b bar is equals to a plus b whole bar. If we define the operation addition on Zn in this way, then we observe that this operation is well defined, okay, and well defined, and it satisfies all the exams of group. This operation is commutative, and therefore Zn is a abelian group. Zn is a abelian group of order n. Particularly, Zn is a finite group. Zn is a finite group of order n. It is a cyclic group. It is a cyclic group. So particularly यहाँ पे हम लोगों को जो Zn जो मिला है हम लोगों को वो कैसा है? एक फाइनाइट ग्रुप है, यानी कोई भी ऑर्डर का हम लोग फाइनाइट ग्रुप बना सकते हैं, और वो दैट ग्रुप इज आवर cyclic group. That group is our cyclic group, or you can say that it is an additive cyclic group. There is one important result. If d is a positive integer, if d is a positive integer such that d divides n, if d is a positive integer such that d divides n, then number of elements of order d in Zn is phi d. Phi d, phi is a Euler phi function. Phi is a Euler phi function. It gives number of non-negative integers less than given integer, that are relatively prime to it. I think I am having very less time, so I will take some fast. Phi of 1 is equals to 1, phi of 2 is equals to 1, phi of 3 is equals to 2, phi of 4 is equals to 2, etc., etc. Okay, now we have I have not given certain idea about this phi function, but here you can pose a question to yourself whether phi 0 exists. If it exists, then what will be the value of phi 0? Phi of 0. In number theory, we say that y is a residue of x modulo m. I hope I should have to skip this. I'm skipping this part because I'm having only 5 minutes. I'm moving to my third part, that is assignment. the first assignment, you please note it, because you are preparing for net and set. So my first assignment, while defining vector space V, capital V, is it necessary to define 1 dot V is equals to V for all V belongs to V? If yes, then why? I will read once again. While defining vector space V, is it necessary to define 1 into V is equals to V for all V belongs to V? If yes, then why? Actually, I have answered this question in my discussion. Now you should have to search where I have discussed this part. Now, second assignment, this is somewhat challenging for the student only, okay? Not for all audience, because I think there are some faculty members are also and students also. So this assignment is challenging assignment for the students only, and I'm going to give you a day for this assignment. Show that, note it, show that 1 plus x square divided by 1 plus y plus z square plus, shall I show it, plus 1 plus y square divided by, in bracket, 1 plus z plus x square bracket close, plus 1 plus z square whole divided by, in bracket, 1 plus x plus y square bracket close is greater than or equals to 1 for all real numbers x, y, z greater than minus 1. I will repeat this assignment. I will repeat this problem. 1 plus x square whole divided by, in bracket, 1 plus y plus z square bracket close, plus 1 plus y square whole divided by, in bracket, 1 plus z plus x square bracket close, plus 1 plus z square divided by, in bracket, 1 plus x plus y square bracket close is greater than or equals to 2 for all real numbers x, y, z greater than minus 1. If any one of you prove this result, prove this, then I will give you rupees 500 as a cash prize, okay, for first correct solution. You may send your proof on my WhatsApp number. I'm giving you, I'm sharing my number. You note it, 9422835707, or you may ask my number to the organizer. They may provide you my number. This problem is open for only students, and for 1 day only. Means tomorrow, up till tomorrow midnight, 12 midnight, you can submit the solution of this proof of this problem. If it is correct, then I will give you rupees 500 as a cash prize, as an award for your work, as an award for your for your knowledge. Now I'm moving to my last part of this lecture, that is motivational concluding part. Getting qualified net and set is not so difficult. While studying post-graduation, you have studied, or you are studying particularly topology, real analysis, functional analysis, classic complex analysis, algebra, fluid dynamics, classical mechanics, operation research, general relativity and cosmology, mathematical methods, partial differential equations, ordinary differential equations, etc., etc. So these each subject or each papers of this subject are equivalent to one NET or set examination. This is my consideration. And I assure you that you have already qualified this NET and set examinations more than 5 times. If you have post-graduated, then you have qualified this NET and set examination more than 5 times. So You have all the support and strength you need. You have all the support and strength you need. So make your own bright future with your own hands. Don't worry what happened in the past. The eternal future is before you. Keep in mind that your every word, every thought, and every deed is creating your accumulations. Your evil thoughts and evil deeds are like a hungry tiger who is trying to grab you, and your good thoughts and good deeds are always ready to protect you with the power of millions of angels. So never lose sight of this uh, invigorating hope, spurtidayi asha, उत्साहवर्धक आशा. So never lose sight of this invigorating hope. I think that thinking is a wonderful power, and it has tremendous power or tremendous energy to do good. So change your thought or change your mind, and that will change your destiny. And that will change your destiny. Before to conclude, I must take this opportunity to express my deep gratitude, uh, that I express my heartfelt gratitude towards organizing committee, especially my friend Professor Dr. Katore sir, for giving me this opportunity. Thank you. All the best and take care. Bye. Oh, I'm having half an hour. I thought I should have to. Anyway, I'm having the material. Okay. So, uh, yes, I will come to the Illuspy function. Illuspy function. Okay. Uh, Residue system modulo M. Residue system modulo M. Particularly, in number theory, we say that y is a residue of x. Y is a residue of x modulo number m. If x is congruent to y modulo m, if x is congruent to y modulo m, x is congruent to y modulo m, it means that m divides x minus y. M divides x minus y. Here we can say that y is a residue of x modulo m, or even you can say that x is residue of y modulo m. Okay. Now, with the help of this residue system modulo m, what is residue system modulo m? This is some part of number theory, but it is again related with algebra. Okay. The set of m integers, let us call R1, R2, Rn, is called a it's called a residue system modulo m if for any integer x there is some ri such that x is congruent with ri modulo m. X is congruent with ri modulo m. In some books you may observe that there are two conditions. Two conditions are given, but I have curtailed one condition. One condition is suffices. One condition is suffices. Now you try to prove this, why one condition is suffices over that second condition. Second condition is not required, or even you can define residue system module m as by using second condition. Here I have defined that, or the set of m integers. Here I have explicitly written m integers. R1, R2, Rn is called residue system modulo m. Is called residue system modulo m if Ri is not congruent with Rj, any Rj modulo number m for all I not equals to j. For all I not equals to j. Means Ri is congruent with Rj. If this happens, then I is necessarily same as j. I is necessarily same as j. So then this these are the two conditions simultaneously given in the definition of residue system modulo number n. But one condition is suffices, either first one or second one. So we can define, we can newly define residue system modulo m as the set of r integers, or as the set of m integers r1, r2, rm, which satisfy one of the condition. The first condition, what is said, that is for any integer x, there is some ri such that x is congruent with ri modulo m. And second condition, none of these numbers ri are congruent with one another except themselves. So now the second part, reduced residue system modulo m, RRSM. If we remove all those elements from residue system modulo m, which are not prime to m, means they are not relatively prime to m. They are not relatively prime to m. Not prime to m means they are not relatively prime to m. What I mean to say over here means, if we have denoted set A as R1, R2, Rn, R1, R2, Rn as a residue system modulo m, and if B is a set of all of the numbers Ri belongs to A, such that the GCD Rim is equals to 1, then B is called as reduced residue system modulo m. Reduced residue system modulo m. Now here actually I'm bowling. You might have a question in your mind. I have changed the topic. Certainly, I have changed the topic, and I have started discussing with number 3. No, actually, my lecture is connected. The number of elements in set B is nothing but phi m, Euler function phi m. The number of elements in B is nothing but phi m. So without searching on net, you try to work out on phi m. It may happen that you may develop a formula to get the value of phi m for any positive integer m. It may happen that you may develop certain properties of phi, whether phi function, this Euler phi function is additive or multiplicative or not, or when it is multiplicative, what are the conditions. I hope you can do this. As I have told you that phi m gives the number of elements in the reduced residue system modulo m. Now, particularly, what is reduced residue system modulo m? I would like to explain with the help of one simple example. If suppose we consider m is equals to 10, yes, 10 is a positive integer which is greater than 1, so we can consider m is equals to 10. Then 0 to 9, numbers, integers 0 to 9, 0, 1 to 9 will form the set of numbers 0, 1 to 9 will form a residue system modulo 10. Now what we will do, we will remove the elements from this set which are not relatively prime to 10. And here we observe that the GCD of 0 and 10 is 10. So therefore it is not equals to 1. Therefore 0 is not relatively prime with 10. The GCD of 1 and 10 is 1. So 1 will be there. 2 and 10 are not relatively prime because their GCD is 2, which is greater than 1. Okay. And 3 and 10 are relatively prime. Therefore 3 will be there in reduced residue system. 4 and 10 are not relatively prime, so we are omitting 4. We are not considering 4 as a part of reduced residue system. 5 and 10 GCD is 5, it is not equals to 1. 6 and 10 GCD is 2, not equals to 1. 7 and 10, yes, GCD is 1, so 7 will be there. 8 and 10 GCD is 2, so it will not be there. 9 and 10, yes, its GCD is 1, so 9 will be there. So how many numbers are there? 1, 1379. 1379. These are the only integers remains which are not relatively prime to 10, which are relatively prime to 10, which are relatively. We have omitted all number which are not relatively prime to 10, and we remain with 4 elements 1, 3, 7, 9. So therefore, 5 of 10 is equals to 4. These are 4 numbers. These are 4 elements. Over here, you will observe that phi1 is equals to 1, phi2 is equals to 1, phi3 is equals to 2. If suppose modular number m is prime number, if suppose even you can prove this, if suppose modular number m is prime number, then phi of m is equals to m minus 1. Then phi of m is equals to m minus 1. That 2 is prime number, therefore phi of 2 is equals to 2 minus 1, that is 1. 3 is prime number, therefore phi of 3 is equals to 3 minus 1, that is 2. Okay, and phi of 5 you can have, particularly phi of 5 is equals to 5 minus 1, 4. Okay, and so on. So actually there is a general formula to calculate directly the phi value or elusive phi function value of given integer, of given positive integer. Okay, but my suggestion is that instead of searching that formula, you try to work out whether it is possible for you to develop that formula or not. Okay, if you will think in this way, then certainly you will develop, you can improve your concept, or you can improve your knowledge and your thinking power too. What is the role of this phi function in algebra? Again, over here there is one very interesting assignment. If you want to note, you may note it. If G is a cyclic group of order n, if G, capital G, is a cyclic group of order n, and if suppose positive integer d divides n, and if suppose positive integer d divide n, then find number of subgroups of order d, then find number of subgroups of order d. Here, I might have told you particularly one result. If if d divides n, then number of elements of order d in Zn is equals to phi d. In Zn is equals to phi d. If d divides n, if n is divisible by d for any positive integer d, then number of elements of order d, of having order d in Zn is equals to Euler phi function d, phi of d. With the help of this result, one can easily calculate the number of number of subgroups of order d in cyclic group, in a finite cyclic group of order g, of order n. So this may help you particularly while solving objective type questions on this topic. This formula may give you a direct answer for of this questions, of such type of questions. Next is unit group. Now, what is unit group? Let n be a positive integer. Let n be a positive integer. Then residue system modulo n forms a group. Then reduced residue system modulo n forms a group under multiplication. Okay. Residue system modulo n forms a abelian group with respect to addition. Residue system modulo n forms a abelian group with respect to addition, whereas reduced residue system modulo m forms a group under multiplication. And this group is called as unit group of units, and this group is called as a group of units. Now, here you might have it, you may not have come across a unit group of units. Now, this concept is particularly you might have studied rings. Okay, in this we call an element A is unit. Okay, if there is element B such that AB is equals to 1, AB is equals to unity, AB is equals to unity, then we say that A is unit element, A is unit element, or B is unit element. So over here we observe that particularly, that is in reduced residue system modulo M, these are nothing but unit elements. These are nothing but unit elements under modulo multiplication operation, under modulo. Is, for example, we have considered modulo number M is equals to 10, and we have found that 1379 are, these are the these are what uh, these are the elements of reduced residue system modulo 10. Now you observe that these elements are unit. These elements are unit. Particularly, uh, one is a 1 into 1 is 1, so 1 is unit, no doubt. 3 and 7, these are unit. 3 into 7, you will have 21 modulo 10, then it is congruent to 1 modulo 10. So 3 into 7 is congruent with 1 modulo 10. Therefore, 3 and 7 are unit. 3 and 7 are unit. And 9 is unit itself. So 9 into 9 is congruent with 1. 9 into 9 is 81. 81 minus 1 is 80, is divisible by 10. Therefore, 9 into 9 is congruent with 1 modulo 10. Therefore, 9 is a unit element, 3 is a unit element, 7 is a unit element, and 1 is a unit. Therefore, these unit elements form a group under multiplication. Under multiplication, congruent modulo n. Congruent modulo m. Okay, so this will form a multiplicative group. This will form a multiplicative group, and order of this group is nothing but Euler-Fire function. Is given by Euler-Fire function. So particularly, if suppose we are having m is equals to 4, then the group of the unit group under congruent modulo 4 is a set particularly. उसमें कौन से एलिमेंट रहेंगे? 4 रहा तो 1 and 3. Okay, there will be only two elements, 1 and 3. You will observe that 1 is unit. 1 into 1 means is congruent with 1 modulo 4, and again 3 into 3, that is 9. 9 minus 1 is 8, is divisible by 4. So therefore 3 into 3 is congruent with 1 modulo 4. Therefore 3 is unit, 1 is unit, and you can conclude that the set of two elements 1 3 under binary operation multiplication of congruent modulo n forms a group, This is abelian group of order 2. This is abelian group of order 2. If you are by changing modular number, you can form multiplicative abelian group. You can form multiplicative abelian group. As I told you, if suppose one want to find out the all positive divisors of integer n, suppose n is equals to 4, और 4 के all positive divisors हम लोगों को निकालने हैं. Then how to find out the all positive divisors? If number is small, then okay, one can find easily, very easily. Okay, is for if suppose our n number is 4, then we have 1 divide 4, therefore 1 is 1 divisor. 2 divide 4, therefore 2 is a divisor, and 4 also divides 4, therefore it is how many divisors are there? only 3 divisors. Okay, 1, 2, and 4. These are the 3 divisors. But if suppose number is large, then how to find out the number of devices, positive devices? Okay, number of positive devices. यहाँ पे negative नहीं बोल रहा हूँ मैं, number of positive devices. Okay. Number of positive devices. So we know that by unique factorization theorem or by fundamental theorem of arithmetic, every integer n can be uniquely expressed as p1 raised to the power alpha 1 into p2 raised to the power alpha 2, etc., pm raised to the power alpha n, where p here particularly p1, p2, p3, p4, pm are the prime numbers or prime integers, and alpha 1, alpha 2, alpha n are the positive integers. Here I'm omitting zero, नॉन नेगेटिव नहीं बोल रहा हूँ यहाँ पे, मैंने वहाँ पे अगर जीरो रहता है तो वो 1 होता है, यूनिट नंबर हो जाता है. So we can say that alphas are positive integers. So if suppose n is an integer, then by fundamental theorem of arithmetic, we will have n is equals to p1 raised to the power alpha 1, p2 raised to the power alpha 2, etc., pm raised to the power alpha n. And then in this case, we can have number of divisors of n, number of positive divisors of n is given by product taken on variable I equals to 1 to m number of वहाँ पे जो primes है, number of primes है n, into in bracket alpha I index of the prime plus 1 bracket close. Particular this formula is again very useful to find out the number of divisions. This is a some part of the number theory built. Okay. Now to prepare this topic algebra nicely, okay, one can refer. I'm having some list of books that is Topics in Algebra by I.N. Hurston. The book is very nice. The author has given certain exercise in this book by marking stars, 2 stars, 3 stars, etc., etc. These stars indicate the difficulty level of the problem. If you will try to read this book and if you will try to solve such type of problem, then I'm very certain that you can develop your concepts. You can learn a topic very easily. So this book is very nice. Second book is Basic Abstract Algebra by Bhattacharya, Nagpal, and Jain. This book is available in market. One can purchase, and price is also comfortable. Okay, affordable. Third book is again, this book is very nice. Contemporary Abstract Algebra by Joseph Gillan. This book is somewhat informative. Okay, and certainly beginners should not have to learn this with this book. After certain ideas, after having certain concept, one may start reading this book. If you will start reading this book, then you can achieve, or you can develop your concept very nicely. Next book is Modern Algebra by J.N. Sharma and A.R. Vaisheshwar. This book is quite old book, but book is very nice. Algebra by Michael Artin, M. Artin. This book is very बहुत ही अच्छी किताब है. आप जरूर ये किताब रेफर करना. I hope this book is almost available in your college libraries. Next book is a textbook of modern abstract algebra by Shanti Narayan and Satpal. This is also a nice book. You may refer. And next book, Abstract Algebra by D. Dumit and R. M. Foot. This is also a nice book. After reading certain, after developing certain concept, you can read this book. Then one more book, again two more books, particularly Algebra by Nikolaevsky and Potapov. This is somewhat a Russian author book. This book is also good. And particularly one book I have amazed a lot is that Group Theory and General Relativity by Moshe Carmeli. This book gives the idea to correlate the topic, or you can establish the relation between certain concept. That is, author has developed means relate general relativity with group. There are so many. Actually, if you will try to read beginners for the at the beginning, if you try to read this book, you will find that it is very hard to get. It is very difficult to understand. But after reading certain abstract algebraic books and after developing certain concepts, you may try to read this book. You will find that the author has nicely present these topics, group theory and general relativity. If you want to ask any questions or if you are having any doubts, you may ask.
Yes, sir.
Yes.
Yes, sir. How
अगर
to
आपको
find the
कोई
number of subgroup of finite cyclic subgroup?
That is actually I have quoted one result. If d divide a positive integer d divide n, then number of elements of order d in Zn is equals to phi d, Euler phi function. Okay. Now there is one more result. If G is a cyclic group of order n, then it is equivalent to Zn for some integer n, for some positive integer n. Okay. Now G is equivalent to Zn, then by using this result, if D divides n, then number of elements of order D in Zn is equals to phi d. Okay. So कितने एलिमेंट मिलेंगे हम लोगों को डी ऑर्डर के phi d. तो phi d नंबर के ग्रुप बन जाएंगे, सब ग्रुप बन जाएंगे ऑफ ऑर्डर डी. ओके, यू गॉट?
यस सर.
समझ में आया? यहाँ पे बहुत ही एक हिडन कॉन्सेप्ट है. यहाँ पे कैसा किया है, अगर कोई भी ग्रुप देखे हैं, G is a cyclic finite cyclic group. Requirement is finite cyclic group, not infinite. If G is a finite cyclic group, okay, then and if suppose D divides n, then then find number of subgroups of order D in G. तो रिजल्ट सिंपल है, phi d निकालना है वहां पे, phi d. ओके, क्या निकालना है हम लोगों को? phi d निकालना है. वो कैसे निकाल, पहले देखते हैं how this happens. Okay, G is a finite cyclic group of order n. This implies that G is isomorphic to Zn for some integer n, for some finite integer n. Okay, and what you know? We know the result. If D divides n, then number of elements of order D in Zn is equals to phi d. So that will be the number of subgroups of order D in G. Phi d represent the number of subgroups of order D in G. बहुत अच्छा सवाल पूछा आपने और एक्चुअली उसका जवाब सिंपल है। ओके, मैंने असाइनमेंट करके दिया था, तो गुड, यू हैव नोटेड दैट। और किसी को पूछना है?
Is there is
आणखी
any
कोणाला
question
काही?
from participants?
So thank you. I explicitly express my gratitude to the organizing committee and my friend Professor Dr. Patore sir. So thank you and take care. Bye.
Thank you, sir, for sharing your valuable knowledge and expertise with us. Thank you for sharing the information regarding NET/SET examination. Thank you so much, sir. Now we are moving towards the valedictory function. Respected dignitaries present here today, a warm welcome to one and all. I welcome Honorable President of valedictory function and Honorable Chief Guest of today's valedictory function, Dr. S.P. Kandalkar sir, former Head, Department of Mathematics, Government Vidarbha Institute of Science and Humanities, Amravati. Sir, please accept our welcome. Please.
Yes, thank you.
Also, I welcome Honorable Guest Dr. V.G. Mende sir, RDIK and KD College, Badnera. Sir, please accept our welcome. Thank you, sir. Without wasting time, may I now request Chief Guest of today's valedictory function, Dr. S.P. Kandalkar sir, to address the gathering.
So, president of this today's program, Dr. Katore sir, and Professor Dr. Mete sir, one of the member of the organizing committee of this university level workshop on NET/SET guidance in mathematics. So, the speaker of this NET/SET guidance are Dr. J.N. Chaudhary, Dr. U.S. Thul, Dr. S.R. Chaudhary, and Dr. Kamal Ingle. So out of these four speakers, I know very well to these three speakers. Dr. U.S. Thul is was my colleague when I was in the Institute of Science, Nagpur. He was my head of department there. Professor S.R. Chaudhary also with me when he was in a Government Vidarbha Institute of Science, Amravati, as to work as a work there as a ad hoc basis. And J.N. Chaudhary was is a very good teacher that I know, and he was a resource person when I have attended refresher course at North Maharashtra University. Now presently that name is changed, Bainabai Chaudhary, North Maharashtra University. So I know all these speakers except this Kunal Ingle. So I think that this workshop on this NET/SET guidance would have been fruitful to the students. So this is to organize such type of workshop is a need of present situation, because as all of you know that without having this qualification or acquiring this qualification of NET and SET, no one can be appointed on senior college as a lecturer, and it is one of the essential qualification. And whenever it was a time that no one that to find out the net set students in this area, particularly in our Vidarbha region, particularly in our Amravati division, Amravati University jurisdiction, Nagpur University jurisdiction. So passing of that net set exam was very less, or no one was there except one or hardly two students were there, and it was a thought that to pass this exam was very difficult, and but though the scenario has completely changed. Now the present situation is such that the number of students of pass these exams are in very large percentage, and to get the opportunity to serve as a lecturer in the senior college is very less now. So there are so many students who have passed this exam but now still jobless, but since this qualification is essential qualification, and after passing this MSc, so what to do next? So this is questions in everybody's mind. So why not to try for this exam? So everybody getting or everybody trying to pass this exam nowadays. So I just say about this NET and SET exam. It is not a difficult exam. You just know how the little hard work, or we say that much hard work is there, and with the hard work and the tricks which nowadays given by the expertise for the options, how to get the correct options for the questions there. So that becomes, this passing of examination becomes very easy. So with the hard work and your sincere efforts, I think that you will pass this examination, but your hard work is must. Otherwise, if you are not keen to pass this exam, or not you are taking this exam lightly, so I don't think that you will clear this exam, because hard work is must. Though you have a little knowledge of the subject, though you don't have much marks on your paper in the MSc exam, but with the hard work and the what we say that the to get the solutions, correct options for the correct question, for these questions, the tricks are there. If you know what about the tricks of how to solve these options, then nothing is hard there. So I think you think about is much. So I think what to say on this occasion. I have joined this just now, and I didn't hear much to these resource persons. We have delivered or given knowledge to the students regarding this NET-SET and NET-SET exam, but this is the need of the time, and I advise to the students, do the efforts sincerely, and as this is the need of essential qualification for to become the lecturer in senior college. So I think student will take it very keenly, and will work hard. So So I think what can I advise you more regarding this NetSet and NetSet examination? I think whatever the knowledge you have gained today, you have gained by listening to this expert, it is sufficient, or you will work in that direction, you will study in that direction, and you will try how to become expert in the solving these questions with the tricks which has been given to you by these experts. So thank you very much for inviting me as chief guest for this program, for this workshop. I thank to the organizing committee. Thank you very much.
Thank you so much, sir. Now, may I now request Dr. Vijay Mehta sir to express their views.
Good afternoon, all dignitaries and participants. Warm welcome to one and all. So, every year, the country celebrates National Mathematics Day on 22nd December to commemorate the birth anniversary of Srinivas Ramanujan. So to develop mathematical culture in our region, our university has started a program of National Mathematics Day from 2012, so that it is helpful for students for competitive exams such as NET, SET and GATE. This workshop is distinguished to enhance mathematical skill. It is one of the most effective way to bring out the best in students and to build skill and confidence and to nature learning. This helps students practice their understanding and applications of various concepts. So I thanks to Dr. Katore sir for moral support for last 5 years to organize such type of activities. Thank you.
Thank you so much, sir. Now, last but not the least, we are moving towards the vote of thanks. On behalf of organizer of the workshop, first of all, my sincere thanks to all organizing committee for making today's event. Thanks to other dignitaries. First of all, I want to thank our honorable chief guest, Dr. S.P. Kandalkar sir, who spent his time gracing the workshop. Today, we had the opportunity to hear your thoughts and is definitely encouraging. I am also thankful to our resource person of today's workshop, Dr. S.R. Chaudhary sir, Dr. J.N. Chaudhary sir, Dr. Kunal Ingre sir, and Dr. Uday Thul sir. It was really very interesting to learn from all of you. Your depth of understanding of user interface and the way of presenting the subject in such an interesting manner is very inspiring, sir. Thank you so much for sharing your valuable time and knowledge with us. I also thank Honorable Dr. S.D. Katore sir for organizing such helpful workshop. I also thank Dr. Mehta sir, Dr. Nimka sir, Dr. Baiska sir and all faculty members from various colleges and all participants in this event. Thank you. Now, with the permission of organizers, the workshop is over here. Thank you so much. And the feedback link will be sent after the workshop. on your WhatsApp. Please share your valuable response. Thank you so much.